AI for security and security of AI. I'm Kathrin Grosse, and I'm organizing this workshop together with Battista, Biggio, and Fabio Roli. And we're at ITASEC. We're going to have two invited talk at this workshop. One is given by Conrad Rick, whom you might have seen. He's already here. His topic is code stylometry, and more in detail how you can attack this inference. And then later we're going to see an invited talk by Florian Tramet about private learning. In general, this workshop has 9 contributed papers, which we distributed into 3 sessions. The first session, which is after Conrad's talk, is about attacks. The second session, which is after Florian's talk, is about privacy. And the last session is about robustness. The first session is chaired by Battista, the second session is chaired by me, and the last session is chaired by Ambra. Thank you a lot for that. And if you have questions, please post them in the Q&A here in the tool, and we're going to ask them to the speaker then afterwards. So we're going to moderate that a bit. And then thank you all for being here, and let's start. Battista, I'm handing over to you.
Okay. I think we are going to share the detailed program with a PDF somewhere.
It's in the Slack channel, actually. If people want to, we can share the link here as well.
Yeah, maybe you can just copy the link in the chat and send to everybody so that we have a complete program as well. It's a bit unfortunate that we didn't manage to have it on the website, but that's the best we can do, and so we're gonna share it here as a PDF file, basically. Okay, so as Kathrin said, the first talk is by Conrad Rick. So Conrad, it's our pleasure to have Conrad here. Conrad is a professor of computer science at the Technische Universität Braunschweig in Germany. And he has many achievements in his career. His research is focused at the intersection of computer security and machine learning. He won the CAST-GI Dissertation Award, a Google Faculty Research Award, and the German Prize for IT Security. The talk is Who Programmed This? Attacks on Code Stylometry. So it's a great pleasure to have Conrad here. Thank you very much for joining us. I'm sorry for these kind of inconveniences, technical issues that we may have, but now I think I can hand over the privilege to Conrad, who can start the talk, and then we can collect Q&A in the Q&A part of the WebEx platform. And then at the end, I can just read the questions loud to Conrad, who can answer. Okay, thank you very much, Conrad. The stage is yours.
Okay, so you can hear me, you can see my screen, hopefully. Okay, tip-top. So thanks a lot for the invitation, and no worries with respect to technical problems. So it's kind of the new normal to have technical problems. Okay, so I'm talking about code stylometry and attacking it. Maybe just a brief introduction to myself. I think Battista mentioned all the important stuff, all these super important prizes, but the truth is, actually, I'm here because I really like machine learning and security, and I'm working on combining these two fields for a long time. And I had a lot of fun, sometimes also a lot of pain with this kind of intersection at different places in Europe. And now I'm in Braunschweig. This is in the middle of Germany, a medium-sized city, and I'm running a small institute there. So what's about this talk? This talk has 2 parts, and these 2 parts are related to the topic of this workshop. The first part will be about code stylometry, and this is, I would say, a classical application of machine learning in the field of security. So it's something that you would expect maybe from this workshop. And in the second part, we are going to attack the machine learning in this application. So this will be about the security of machine learning. And I hope that by having these 2 topics here, I somehow fit into the theme of the overall workshop. So the first thing that you might ask is, what is stylometry? It's sounds like an interesting, cool world, but what does it mean? And actually, it's not a fantasy world, but a real world that is used in forensics and in linguistics. So if you have a written text, let's say some book or some piece of paper, you can analyze the words, the grammatical structure, and all of these things, and try to find out who's the author of this book or document. And this is the process of describing the style of writing, and this is why it is called stylometry, somehow measuring and analyzing the style of written text. And it is not only some fantasy thing, but it's used regularly by the police. So if you get blackmailed, or if you, I know, there's a robbery and the robbers leave a letter somewhere, then the police will investigate what's written on this letter, what is the style, can we infer information about the authors from this written text. And code stylometry is basically translating this idea to source code or even to binary code. So in other terms, given some software, we want to know who has written it. And of course, you can imagine that for malicious software, for software exploits, and all sorts of other things, it is very interesting. I also have to say that this application has a good and a bad side, and I'm not talking about these sides, but you can imagine you can do this for good by finding malicious people, but you can also do this for bad. For example, by searching people that developed some interesting privacy-preserving software and then go after them. So with many techniques in security, there's two sides. So let's just look how this works and what the actual problem is. So here I have an example for you, and I chose an example that is quite typical. So it's not this beautiful code that you can see in a textbook, but it's this really ugly spaghetti code that you have to deal with in practice. So here we can see the C++ mess. And the question is, has Alice, as an example, written this code? And if we know Alice, maybe personally, we have worked with her, maybe we can identify this. But if we haven't any much knowledge about Alice and her style of coding, it's super difficult to understand what's going on here, especially if the code is so dense and ugly. And an idea that came into play maybe 10 years ago, why not use machine learning for this task? And in fact, this is a perfect example of how machine learning can interface with security, because we have some data, so examples of known code from known persons. And now we take this known code and use it to train a classifier. And the goal of the classifier is to find out if there's an unknown piece of code, has it been written by somebody from my label training set, or is it maybe an unknown author? So in principle, most of these approaches are learning a classification with a rejection class. And this is a standard application of machine learning. Now, the first thing that people started to look at is how do we model the source code or the software such that machine learning can work with it? And different ideas came up. So, for example, people started to look at lexical things. So you maybe remember compiler engineering, there's different stages. And one of the very early stages when you compile a software is a lexical analysis. And the first idea was use this lexical analysis and try to infer information for machine learning from it such that you can train a classifier. And at the very core, this boils down to analyzing a stream of tokens. In compiler engineering, these tokens are called lexems. Of course, then people thought, if we have already a compiler, why not go one step further and look at more involved structures? So for example, people started working on the abstract syntax tree, which is a standard representation when you compile a piece of software. And it's essentially a tree that describes how the software matches the grammar of the language. And all compilers use this very representation for doing syntactic analysis of source code and software. In this case, the input is a tree. And then there were some, I would say, not so clever people that said, we can also do something else. We just analyze the layout of the code. So are there many white spaces? Are they using tabs? Are they using 4-tab indentation or 8-tab indentation and things like that? Now, we know, and I guess also those people know, that these features can be very, very easily be changed by anybody, right? If you have an integrated development environment, an IDE, you can basically define the layout of your code, and then your code will always have the same layout. So for this talk, I'm ignoring this work because I think it's not really suitable to make any reasonable assumptions about the authors. For the other two types of features, let's see how they can be taken and somehow changed such that they are accessible by learning algorithms. So let's look at the lexical features, the lexical tokens. So the code is lexically analyzed. Typically, this is done with regular expressions, by the way. So we are not in the phase where we really analyze the full complex grammar of the language, but we're rather looking at the individual elements, the so-called tokens, lexems. And this is done with regular expressions. And it gives us access to many things that play a key role in software. So for example, we can see the types as individual tokens. We can see keywords. We can see names. You can see the brackets. Often I left them out here, but you can typically also see them. So you get something like a rough overview of what is in the code. And implicitly in this information is also the syntax and the semantics of the code. And this was kind of the first idea how you could kind of get access to the code to learn from it. And in its core, this is very closely related to classic natural language processing, where you have just a stream of words and you do simple things like back of words or embeddings. So this is the first strategy. The second strategy is to take the syntactic structure into account. So here you would use a compiler and generate an abstract syntax tree. And then you can work with the elements of the tree. So for example, you can extract subtrees of a certain size and then use these subtrees to represent the source code that you want to analyze. Here in this example, you can see the syntax tree is already a little bit more complex. So you can see all the different structures. There's a declaration in the beginning. Do I have a pointer? I hope so. So this B here is declared. Here you can see the if statement. You can see a function call. You can see an operation in a return statement. And all of this is captured in this tree. And as a result, you get a very generic and very comprehensive representation of the software. There are more advanced representations that tell you something else. So for example, a control flow graph or data dependence graph or program dependence graph. But all of these are generated from the abstract syntax tree. And thus it forms something like the very, very basic representation of code in a compiler. And just as a remark, when we did this for binary code in 2018, we tried to somehow reconstruct the AST using decompiling techniques from already compiled code. So we knew about the importance of this representation. So instead of working on the binary code directly, we tried to create this structure because it's so powerful. And the next step that remains is taking this structure or taking the stream of tokens and getting it into a vector space, because most of the machine learning algorithms operate on vector spaces. Or if you want to be super picky, you can say maybe they work on, I don't know, Hilbert spaces or things like that. But for simplicity, we just say it's always something very closely related to a vector space. And one thing that people did is they used back of words models. In these models, you have several dimensions. Each dimension is associated with one word. In our case, it could be a token or it could be a subtree. And then you count how often this word or subtree appears in a piece of software. And this results in a long vector that tells you something about the content of the software. Or what people also did is use neural networks to learn different types of embeddings. So here you're basically trying to find an lower dimensional representation that enables you to see similarities by having small distances within this learned representation. And on the bottom, you have something like the typical workflow in all of these papers, and they take a piece of source code, they do this embedding or mapping, and then they learn a classification. So here, as a very simple example, I just plotted a classifier that separates the feature space into different regions. And in each of these regions lives one author, green, blue, red. Or it's not red, but anyway. The task now is, if there's a new point, it's mapped to the vector space. And if we have trained the method well, we can see from the space where it lands, it's either author A, author B, or author C. That's how these approaches work. And surprisingly, they are super effective. And actually, they are even scary in effectiveness. So to give you here an example, 4 methods from recent years, not completely, this is already quite old, but 2017, 2018, 2015, and there's even more work. And most of these approaches end with an accuracy of over 90%. And surprisingly to me, also the number of authors that can be discriminated has grown tremendously. So in this work here, the researchers can classify over 8,000 authors with very high accuracy. And what does it mean? It means that, unfortunately, we as humans leave a lot of artifacts of stylistic patterns in our software, and we are identifiable by these patterns. And of course, we can argue about overfitting or complexity of learning models, or we can argue about the design of feature spaces. We can also argue about the design of the experiments, but I think from these results, it's already clear that there is something in the code that allows to discriminate and identify people. And when I first saw this, I must say I was a little bit shocked because I haven't expected this. So I was assuming that we more or less program in the same way. And I also, and now this is the second part of this talk, and maybe also a little bit longer, of course, I was also skeptic about the robustness. And if you read through the papers from these authors, they basically say the problem is solved. We can now use this technology to find malware authors and identify programmers. And I thought, no, this should not be the end of the story, and it should not be that simple. So for the second part and the little bit longer part, I want to tell you about how this can be attacked. So we want to switch sides now. We are maybe malware authors, or maybe we are just privacy advocates or privacy-friendly people, and we want to make our code an attack such that it is incorrectly attributed. And of course, we can argue whether this is a valid objective for research, but it's definitely an interesting and very, let's say, fascinating idea to apply techniques from adversarial machine learning onto this problem. I don't have the time to talk about adversarial machine learning, and I also expect that most of you have heard about it, and that many cases here have to do with vulnerabilities in learning algorithms and how these vulnerabilities can be exploited. And by far the most prominent vulnerability in machine learning methods are so-called adversarial examples. And although the origin of this vulnerability is still not fully understood, it is pretty clear now that many algorithms are vulnerable and that often very, very fine changes can cause these vulnerabilities. So as an example, what's going on in these attacks? So look at these 4 images. You can see an airplane on these images. And if you add a little bit of noise, a little bit of specifically crafted noise to these images, they will cross the decision boundary of machine learning algorithms. So in my small picture here, this blue point crosses to the other side, and then it becomes something else. So this small noise, often called a perturbation, fools the learning algorithms and leads to incorrect predictions. And there's like thousands, in fact, thousands of papers published on this very topic. I would say several thousand study variants of this attack, and other thousands propose defenses where unfortunately most of them do not work that well. So it's a really difficult, interesting, and fascinating problem. initially it was thought to be a problem related to neural networks, but now we know that also many other learning algorithms suffer from this vulnerability. And people like it because these images are very easy to see. So I hope you can see the little bit of noise in the 3 examples. And you can see that once it's detected as a car, as a dog, as a truck. And you also recognize that this noise for a human has no meaning, whereas for a machine learning algorithm, it changes the decision boundary and creates a wrong prediction label. And now our idea was, okay, this is cool, but we want to apply this on the level of source code. So we do not want to apply this on images. We are not experts in computer vision, but we have some experience with source code, analyzing source code. So we thought, okay, let's generate adversarial examples of source code. And the naive idea is, well, you have the source code, and in the source code, there is this small noise. Here, these red keywords, and they mislead the classifier, and voila. This is attributed to Alice, although Alice has never written this code. Or the other way around, Alice has written the code, but she has added this little bit of noise such that it's now classified as being written by Bob. Yeah, and we could use this, and others, maybe intelligence agencies, could use this to make a lot of very bad things, evading attribution and maybe attributing somebody else, like the Russians would attribute the Chinese hackers the American ones. And if this would be possible, attribution using machine learning should not be used in practice. So we started and defined something like the, I would say, attacker model. So what do we want? How should the attack be formally designed? So first we thought, okay, like in adversarial examples in images, we can have 2 objectives. So either I want to hide myself, so I just want to change the prediction to some other developer, not myself, but it doesn't matter who's instead chosen. This is called an untargeted attack. And the other one is, I want to attribute the software to somebody that I maybe don't like, to Bob. So I'm, as Alice say, this crappy piece of code, I want to make sure that it is classified as Bob because he writes this bad code and I'm going to attribute it to him. This is a targeted attack. And then we thought about constraints. So can we do anything? And we thought, when we looked at literature, it's not okay if, for example, Alice pastes a long piece of code from Bob onto her software. And it's dead code, it's just added. And we thought this is too simple. And also it could be detected easily. So we wanted a smart attack. And we thought we have to do a more realistic setting. So here are essentially our 3 main constraints. So first, we did not want to change the semantics of the program. So whatever we do with the code, it should perform exactly the same task. No excuses, right? It's not that it can do a little bit different. No, it should perform exactly the same tasks. Otherwise, it's useless. You will later see that it's a strong constraint, right? The second thing is, if somebody looks at the code, it should be plausible and the changes should be minimal. Similarly to vision, where this noise should be very fine and not visible, we wanted our code changes to be also very fine and not visible. And this means that simply adding, for example, a lot of code from Bob to our example doesn't work, because if somebody looks at the code, he or she would see that there's something strange going on, because most of this code is never used and doesn't really fit for the problem at hand. And the third constraint was that we said, okay, we do not really know how the defender or the attributor is working. We do not know the machine learning algorithm. We do not know the architecture of a neural network or things like that, or we even do not know the features. All that we know is that if we send something to this classifier, we get back a response, and the response is something like a probability or so that indicates what is the predicted developer and how sure is the algorithm. This is a typical setting for black box attacks. It's not a perfect setting because in the real world, you would not even get this confidence. So you would only get a prediction. And sometimes you might not even get the prediction. So for example, if the police is hunting you, they will not tell you in advance that your code has been classified, but it's a reasonable assumption that most researchers do to get hold on these black box attacks. So we built it like this, and then we stumbled on a problem. And we were, so to say, a little bit naive. We thought there's like 1,000 or 10,000 papers on adversarial examples. So all that we have to do is read maybe 10 or 20, yeah, or maybe 100, and then we will have a very good idea, and then we can apply the idea and change our code. But unfortunately, the vast majority of this body of research deals with changes in the feature space, in the vector space where the machine learning works. So in my example here, all of these attacks basically move around in this space. So they change vectors, do a little bit left, do a little bit right, and things like that, which is cool and great. But unfortunately, from these vectors, there's no way back to a working piece of source code. So for example, if you know that there's like 3 times the type int and 3 times the type double in a program, you cannot synthesize a program from this knowledge. It's just too much information that is lost by embedding the data into the vector space. And also making something up is so challenging and likely will also violate our constraints. So we will end with ugly, implausible code that looks suspicious from the start. And it turns out that reconstructing source code from the embedded vectors is a super hard problem. And in most cases, I would say it's impossible. And those people that did this in this large set of papers, either they made some constraints to their advantage. So they said like, I can add code at the end. Yeah, then you can do it. Or they said like, oh, there's a one-to-one mapping of a certain part of the software. So I can use this one-to-one mapping to go back. But if you take arbitrary code, I would say that there's no feasible mapping from vectors back to the code, unless we have a completely new way of embedding data into a vector space. So this was a little bit a downer, and also the start of some interesting research ideas, and also a cool paper. So the idea was, if we cannot move in the feature space alone, we have to move also in the original source code domain. So we have to define something that allows us to move in source code. And moving means that we transform the code such that it preserves its semantics. So it's doing the same thing, but it changes its appearance. And you can see this here on the bottom. So we start somewhere here, and then we do different transformations. And for each of these transformations, we check where does it end in the feature space. And then we pick one point. And then our idea is that we somehow guide the analysis towards our target. So we know that we want to reach this point in the feature space. So what we do is we pick one transformation, and then from the new transformation conduct another set of transformations. Then we end here. Then from there we go to this point, and then over multiple iterations we transform the code and at the same time move in the feature space. And I think this is an interesting idea. It's wasn't completely new at that time, I would say, because somehow people did this implicitly. So they didn't know that they were working in both spaces at the same time, because maybe they were only working in the source code domain. But underneath, I think all of the attacks that are effective in the problem space build on jointly working in the two domains in parallel. And technically, we did this with a set of transformations. I will show you how they look, and a search strategy that has been very successful in gaming, not in gaming like Doom and Quake, but more in gaming like playing Go and chess. Yeah? And this is Monte Carlo tree search. This is a standard, very powerful search algorithm. And we need this search algorithm to basically decide how we do the transformation such that we move in the feature space. So let's look at the transformation. So here's an example of how we can change the code. So we developed, I think, about 40 or 60 transformations for C code. This was a lot of work because these transformations should be semantics preserving. So if you replace an integer with a different type, you need to pick a type that makes sure that the program still works. So you cannot replace an integer with a char, for example, because a char has 8 bits or maybe 16 bits, but an integer likely has more bits and things like that. So, and we implemented this as part of CLang, which is a compiler front end, and we had a lot of fun getting used to this compiler engineering world, which is an own topic on its own. Anyway, so here's an example of a very small code snippet that has been transformed with 3 semantics preserving transformations. So first, we changed the type. Those of you that program C and C++, they know there exist different types which are equivalent. In fact, they are type defs. Yeah? So they are really the same. But of course, from the outside or for the machine learning algorithm, they look different. So for example, int, depending on the CPU architecture and the compiler setting, might be equivalent to int32, right? So it's a signed integer with 32 bits. Of course, you can take control flow structures like a for loop and change the for loop into a while loop completely automatically, right? So here we changed the for loop into a while loop. We can also do this the other way around, and we also did changes for if statements, for switch statements, for return statements, and things like that. We also did something like function outlining, function inlining, so all of these things that you can do with source code such that it looks different. And we replaced the API, the functions that are called, if there exists alternatives. So here, for example, you can see this in my world, I would say ugly C++ output. C++ programmers would say this is very beautiful. And on the right side, you can see the transformation, completely automatic. Here you can see printf, which I as more C person would say is more beautiful, where the C++ programmer would say this is really ugly because you have to define the type and things like that, which happens automatically in C++. And it took us, I would say, 4 or 5 months to build all of these transformations such that they can be applied to arbitrary C code. And then on top of these transformations, we implemented the search strategy, and we used this Monte Carlo tree search after we played with several other search algorithms. So starting with random search, going over to hill climbing. So this is a very simple search strategy or optimization strategy, going to simulated annealing, and eventually ending on Monte Carlo tree search. And the reason is, or maybe the reason is why this works so well in our setting, is that our attack is a little bit like a game. So we are basically playing with the attribution method. We make a transformation. This is the move. And the attribution method, the machine learning method, tells us how good the move is. And ultimately, we are interested in a series of moves, a series of transformations that let us win. And winning means crossing the decision boundary. And if the machine learning tells us something about its confidence or maybe the distance to the decision boundary, this can be thought of as a very simple game with one person making moves, transformations, and the other person saying, good move, bad move. And it turns out that this worked very well and that we were able to reach winning states rather quickly. And to tell you a little bit about how the algorithm works, I'm not going into all details here, it's also maybe a little bit boring. So Monte Carlo tree search builds something like a search tree this is a little bit like a search tree in games. So you maybe know from chess or other games that you can build a search tree and then look for different moves. So actually the nodes are the states of the game and the edges are moves. And in our setting, the nodes are the states of the source code. So each node corresponds to one version of the program. And the edges are transformations that change one source code into another, preserving the semantics. It does the same thing, but it looks different. And then, of course, we can make multiple transformations. We can also make multiple transformations on one edge if we want to. And the algorithm proceeds in different stages. So here I have plotted the two important stages. In the first stage, we do an exploration. So we test different transformations and then check which is the best setting so far. And this would mean we end in some node U. And then in the next expansion phase, we would use new transformation from this node and then go further in the search tree, generate more states. And after this phase, we would go back to the top, propagate information about how well we have played to all the nodes on top, and then run the selection phase again. And if we are lucky, we end again in the same branch, but it might be that after all of these changes and this propagation, another branch in the tree is more promising, and then we would go there. So this is essentially how this algorithm works. And the difference to any greedy algorithm is that we're basically exploring and selecting the best iteratively. So it's like a balanced move, a little bit like a human maybe. So in complex games, you wouldn't immediately go for winning the game, but you would also go for making strong moves that might not result in a win, but that give you a strong position for later moves. And a little bit, this is the same setting here. So we're looking for transformations that move us very far in the direction of the decision boundary, not necessarily crossing it in the first set. Yeah, we were at this point, so to say, done. We were super happy. We wrote a paper on this. And of course, once you start thinking about a paper, you need to think about evaluating what you have been doing. And you need to think about how can I make this convincing and how can I design the experiments such that they really show that the attack in our example is successful. So what we did is first we reproduced prior work. So we took the previous examples, read the papers, and rebuilt two of the systems, both with the help of the authors from the systems. So I have to say thanks. I think it's hard for researchers if you get contacted by somebody and then somebody says, oh, we are attacking your approach. Can you provide us with information on your approach because we want to destroy it? But they were very nice and helped us, although a little bit reluctant. So they were not super happy about this. And then we collected data from a competition at Google, the so-called Google Code Jam competition. This is a programming competition where thousands of people solve the same programming tasks. And they do this on C and C++ code. So essentially you have people all over the world, they work on the same problems, and the best solution is the quickest one, but ultimately all of them have the same semantics. So these programs do exactly the same thing, and there also exist test cases to check that they work properly. And this is a perfect playground for us because we do not want to learn something about the semantics of the problem, but we want to have several authors that have developed the same or solved the same problem. Because in this setting, the difference between the code can only be the personal style or the personal preferences of the developer. It cannot be task specific. So we picked 8 challenges from this data set for 204 developers, so it's 1,000 samples. And then using this data, we reproduced the results, and surprisingly, it worked on the first run. So we were able to recreate everything in the papers, so okay. And then we implemented our 2 attacks, the untargeted and the targeted attack. And let me show you just some of the results. So this is I think it's a plot that is not necessarily a plot, because it shows basically for the untargeted setting, we succeed with our attack in all cases. 99.2% of the developers can be changed to somebody else. And on average, only 1 to 5 lines of the source code need to be changed. And this is something that I found surprising and also motivating. So apparently it's not so simple that everybody of us has a very unique programming style, but in fact, the machine learning relies on very brittle, subtle artifacts in the code. And if these artifacts are changed, then they are not sure anymore whether this is written from you or from somebody else. So by doing these transformations, we were able to find those small spots where we can change something and then it is incorrectly classified. We went one step further and also experimented with the targeted attacks. So in this setting, we always selected pairs. And then we wanted to go from one developer to the other through a series of transformations. This did not work in all of the cases. So in about 20%, we could not change the style. And we analyzed what was going on. And in all of these cases, we didn't have the right transformations in our hand. Some people do very strange things in code. And if you do not have a corresponding transformation that somehow breaks this pattern or removes the pattern, you cannot get rid of it. And therefore, I would say that once we would have these transformations, we could also change the style of these developers. But for the remaining 80%, we could change the style. We needed more lines of codes to be changed. So between 1 to 10 lines on average. So that's more. 10 lines is already, for these code competitions, something like, I would say, 10% or so. These tasks are not very long, but 10 lines is something like 10% or 10%. And as I said, some patterns could not be forged. Again, we could mislead both approaches. And remember, we did not consider anything about how they work internally. I didn't even talk about which of these approaches uses a neural net and which of these approaches uses a lexical and which uses syntactical analysis. Because for our approach, this doesn't matter. For completeness, I can say Khaliskan is an approach using syntactical features with a random forest, and Abu Hamad uses a neural embedding of lexical features. So here's an overview. So you can see the changes on the level of features. And you can see that in contrast to the lines of codes, many features changed. So this means that if you take one line and make a small and clever change to it, it can result in a lot of different features in the feature space. And this might also explain this complex relation between the two things and why it's not possible to go back and forth, because one line of code might contain 20, 30 different features, including trees, including types and things like that. And this is something that I don't want to miss here. We also did a small plausibility check, because we said in the beginning, we want the code to look normal, okay, right? So we asked a group of students and people from our team, can you please look at this source code? And can you tell us, is it suspicious or not? Is something fishy going on or not? First of all of them complained about how ugly the code is. We said, yes, that's not part of our study, but yeah, often the examples are really ugly. But it turned out that our transformed examples could be detected with 60% accuracy. And in our study, this was a little bit about little more than random guessing. So overall, we concluded at this point that the transformations are plausible in most of the cases. I have a complete example for you. So here you can see, yeah, it's not complete, so there's some dots in the middle, but you can see on the left side the original version. Yeah, you can see this typical C++ madness. And on the right side, you can see the transformed version that solves the same problem. passes all test cases, but has different syntactical elements. So for example, it uses a type def in the beginning. It uses a while loop instead of the for loop. It uses a different API. So instead of C++ output, it uses printf. And declarations have been moved from inside the loop outside the loop. And yeah, I think both of these examples look similarly ugly, but they also look both rather plausible. So it's not that I would say the right one is manipulated or tampered with. I think they have similar characteristics. So this brings me to the end of this small view on these attacks and the problem of stylometry. First of all, let me recap. The stylometry thing is a very cool playground for machine learning. And although I presented an attack, we are still working on this because I think it's an interesting and also challenging area for machine learning, because source code has so many facets and is so difficult to handle. In contrast to maybe pixels in an image, the code has a very fine, complex structure. And from compiler engineering and software engineering, we know many, many tools that can work on this data. So it's an interesting and promising area for bringing machine learning to this area of software engineering, compiler engineering. And then, of course, our attack is an example of an adversarial example for source code. It builds on a new strategy for doing these attacks. The outcome, however, is the same. The machine learning methods are misled. They make incorrect predictions. And the bottom line here is that this code stylometry is not reliable. It's not robust. And if people really want to use this in intelligence agencies or to find super smart criminals, this will definitely fail, because those smart criminals, they know about this work, hopefully they are in the workshop right now. So they listen to these talks, they read all these papers, and therefore, if we really want to find spies and agents with these techniques, I'm quite sure that they will use all tricks to do wrong attribution. And I mean, I know this from the malware domain, maybe as a last remark, there is already something like this going on. So often, if you take real world malware, you find, for example, Russian comments or Russian strings in the code. And then the question is this a Russian malware, or is it just a malware where somebody placed Russian things into it? Or, for example, often people analyze the time zone of the files and the compiling environment of malware. There's information about the time zone, and the time zone can tell you something about whether this is from the Western or Eastern world. But again, it's not clear whether you can trust this information. And the same holds, according to our study, on source code attribution using machine learning. So with that, I'm looking forward to your questions. Yeah.
Thank you, Conrad, for this nice talk. And I wish you could hear the applause, because we have more than 120 participants here, but unfortunately, we cannot see them. So we have a couple of questions in the chat. So I think one is from Luca Demetrio. I think he's also on the panel, so probably he can show up and ask the question himself.
Hello, can you hear me?
Okay.
So, okay. So first of all, really thank you for the talk. I really liked it a lot. And also, I mean, we share like the Microsoft challenge at some point. So I was so happy to see again, this particular topic and see you like in person. So I'm so happy right now.
Okay.
And so the first thing I want to ask is, basically, so you said that you applied like the technique on the abstract syntax tree of code, and then instead of like applying tree, like and this technique on assembly, you decompiled the code and then applied all the pipeline you described. So I have two questions about this. The first one is like, that was, I mean, you did that because it was too difficult to apply like abstract syntax tree representation on assembly code / control flow graph representation of assembly code. And second is, if you try that, how much, I mean, how much style is destroyed by the compiler? Because I mean, if I write some code and the compiler compiles my code, then basically it's just mixing my style and the macro of the compiler. So I'm wondering how much of the original style of the developer is kept inside the assembly code.
Okay, so maybe there's first a small misunderstanding. So our attack was performed only on the source code. So we
sorry, I was thinking about the first part of the talk. I'm sorry. It's not
no
on the
problem.
attack, just on me. Sorry.
No, I just wanted to make sure that this doesn't sound like we are basically doing back and forth, compiling, decompiling.
No, that was
we're not so cool
clear.
that no, but so for this paper on the binary code, we experimented with many things. So we started with disassemblers, and we thought that maybe we can learn from, I don't know, basic blocks and things like that. It turned out that surprisingly, those high-level features, like from the abstract syntax tree, are more robust with respect to the compiler. So the compiler does several things, like maybe exchanging instructions or playing with registers and, I don't know, CPU pipelining, whatever. But it turns out that if a decompiler goes over this, and maybe basically tries to go back to, is this a while or is it a for loop? This helps.
Okay, nice.
And also the types, I thought in the aftermath, also this with the types that could help. So if you take the source code, the developers can use type defs and they can define their own types, or they can define stupid types. So for example, they can use a long int where there's only a 1 written to it, or a 0, right?
Okay.
And if the compiler will correct this, so the compiler will see or might see that a variable is small, and if you decompile it, you get the small variable back. And we were, of course, training also on, for training, we were also decompiling binary code. So we were not training on source code and then testing on binary code, but we were training on binary code and testing on binary code.
Okay.
So I think we removed a little bit of the noise from the source code, and this gave us more features on these syntactic structures.
Okay. Wow, that's cool. Thank you.
Okay, thanks for the question. I think we have another question from the chat from Sinlong Chang. He's also in the participant list. I'm not sure if he would like to ask the question himself or if I have to do it.
Hello.
Hello.
Yeah, because when I listened, when you say the code is ugly, I just wonder, like, if you pass the adversarial into a standard like formatting tool, will it actually lower the success rate of the attack? No.
So I said in the beginning that we ignore the layout of the code. And to do this, we basically passed all examples through a code indenter, a code beautifier, so to say. So all of our examples had the same layout, the same way that brackets are set, the same way that white spaces and tabs are set. So this was kind of abstracted from our experiments. And with ugliness, I'm not talking about the layout, but I'm talking about the way this programming is done, C++ and C programming. I mean, once you get used to other languages, like Python, for example, you notice that this is a very, I don't know how to say. I still love programming in C, but it's a different way of programming.
So another question is this entire org only done on C++, or is it also applicable to another languages, right? Because if it's on Python, then there was less, because you have basically less thing you could change from, right? Because there's no need to define basically the data type, those type stuff. So
yes. So we didn't do any other language. So we worked with C++ only, but the attribution methods, so those methods that I mentioned, there also exist many for other languages. So for example, there also exists an approach for author attribution on Python or Perl or PHP. So on the one hand, this has been done. The question is, can these attacks be transferred to the other languages? And I don't know. And I must admit also, it requires to do these experiments to go deep into the structure of the language. So you would need to change a Python interpreter or Python compiler or PHP compiler or Perl. I'm not even sure if Perl is compiled, by the way, but anyway. But in any case, you have to go into this kind of software. And if, I think this would be very interesting for people that have experience with these languages.
Oh, thank you so much.
Okay, thank you for the questions. We have one from the Q&A panel. So from Tamo Kruger. So the question is, have you tried to use the adversarial examples to train a more robust stylometry classifier?
So first of all, greetings. We are thinking about this, but we don't know yet how we will do this, or because it's already known that adversarial training, by just taking the one attack and then training with the attack and then running the same attack, seems to work, but only small changes to the attack will suffice to break the system again. So it seems that adversarial training is not so trivial, and in our setting, also generating these examples takes quite long. So one example with Monte Carlo tree search takes about, 8 hours. So generating a pool of, 1,000 examples would take some time. And we are thinking about how this could be done, but we don't know yet.
Mm-hmm. Okay, I don't have other questions. Oh yeah, maybe there's one from Fabrizio Biondi. I'm gonna read it. There's still time for a couple. So the fact that we can shift attribution just by changing a small number of lines would imply that we probably shouldn't use ML-based attribution at all, since it's so fragile. Is this your recommendation?
Yes. I mean, ultimately, I would also ask whether it's possible at all to attribute code. So because, I mean, my philosophical story here is maybe for written text, it's extremely difficult to automatically change a written text such that it's still well read and preserves its semantics. So to my knowledge, this is not solved yet with new cool learning things. But for source code, many transformations. So we are not even experts in compiler design. So there exist many techniques for transforming code. And I would expect that you can trust nothing in a piece of software because everything can be automatically changed. Yeah. So you got the absolute take-home message here. Don't trust machine learning.
But that's it's also outside of the not just for this application setting.
Yes.
I was wondering, so sometimes we also had a couple of similar papers on manipulating code and so on and so forth. And one thing that we always get from the reviewers is that code obfuscation will do a similar effect on the code. So do you think, have you tested like code obfuscation for the same purpose?
Yeah, we also, that's also some of these arguments. But the reality is, of course, that you cannot always use code obfuscation. So for example, if you're developing open source software and you want to be anonymous or you do not want to be detected, you cannot obfuscate your code. We also work with obfuscated code, and this would maybe be a little bit too long here, but it seems that the answer to whether obfuscated code can be attributed or not is not entirely clear. So if you do this naively, even the attributed code can be, the obfuscated code can be attributed. And so you need to take special care that the patterns are really removed. And this is not so simple. What you can do is, of course, encrypt the code and unpack it at runtime. This will always work. But if you just want to change the source code without packing, it's surprisingly difficult.
I agree. I mean, we had similar insights on different tasks. Okay, I think there's no other questions from the audience. We are perfectly on time, so I'd like again to thank you very much, Conrad, for your comprehensive talk. And yeah, let's give you just a big applause, virtual applause for you, and hope to see you soon somewhere. Okay, bye-bye. I think it's time to start the first session of the workshop, where the first talk is, so this is a session about adversarial attacks on different problems. And it nicely follows the talk by Conrad of modifying samples in the actual problem space, not just pixels in images, right? That you can also manipulate in the feature space. So the first paper is by Fabio Pierazzi. Let me see if I can hand over the privilege to him. So Fabio, welcome. I think you can share the screen. Can you talk?
Yeah,
Okay,
let me try.
cool.
Do you hear me?
So yes, so this is intriguing properties of adversarial machine learning attacks in the problem space. Fabio Pierazzi is presenting, and this is joint work with Fergus Pendlebury, Jacopo Cortellazzi, and Lorenzo Cavallaro. So Fabio, the stage is yours. Thank you.
Thank you very much. I'm very excited to be here to present this work, and I agree with you, Battista, that it is kind of very on point that I'm allowed to give this talk after Conrad's presentation. Indeed, actually, even Conrad's work was one of the work that inspired us also to do this work about introducing more principled reasoning for problem space adversarial attacks. So let me start by just recapping briefly what are traditional feature space attacks. In these attacks, you have an original image with feature vector X, and you apply a perturbation delta to the image that corresponds to, I mean, at least in the image domain, it corresponds to imperceptible noise, and obtain an image with feature vector X plus delta that is highly misclassified with high confidence. I mean, this is a very traditional example that is given. I mean, I'm sure that many of you are familiar with this example of the panda. But in practice, mathematically, what happens, I mean, we can kind of simplify it as, well, it's in many cases, it's just an optimization problem in which you want to minimize the pixel perturbation delta according to some notion of LP norms. And most importantly, the loss of the target class, which is basically the loss of the class in which you want an example to be misclassified to. And okay, I didn't mention that I'm focusing right now on evasion attacks. So it happens all at test time. We just want to modify an object at test time to have it misclassified. So let's now consider what happens in the problem space. So also Conrad introduced some of this terminology in their work. If we still use the software reasoning, you can think about the problem space as the actual code and program. And the feature space is just a numerical abstraction that you feed to a machine learning classifier. As an example of feature space, you may have like presence or absence of APIs. And in this context now, so if we look at the problem space about the adversarial attack in the problem space, it's a little bit more unclear what is the actual perturbation that we want to create. And the optimization problem, also, if we look at the formulation for the feature space attack, now we may not be interested anymore in limiting the feature space perturbation, which was in images related to kind of how many features you were modifying. In practice, we may be interested in different things, like does the look code plausible? Does it preserve malicious functionality? Is it still realistic upon inspection, as Conrad also was discussing in his talk? So what you would usually do as a procedure to find an adversarial example is like go from the problem space, use a feature mapping function, move to the feature vector X, find the perturbation delta with an optimization function to find the adversarial vector X plus delta. But then the problem in domains such as software is what is called as like inverse feature mapping problem that basically is a problem by which if the feature mapping function is neither invertible nor differentiable, you cannot go back from the feature space to the problem space. If your feature space is just represented as like presence or absence of APIs, then I mean, there is an infinite possibility of programs corresponding to it, but they are not necessarily realistic or resembling any property of the original app. So in this work that we presented at IEEE Security and Privacy 2020, we made two major contributions. The first one is about formalization, which is a reformulation of adversarial attacks while considering the problem space. In practice, we also unveiled some relationships between the feature space and the problem space attacks. And the second contribution is about, sorry, this was, the second contribution is about
sorry, Fabio,
developing.
to interrupt you. Can you increase the window size?
I can try. Are you seeing it very small? Does it
Yes.
change anything?
Yeah. If you can increase it, because we got some messages that it's too small.
Okay. Is it increasing in practice also for you?
Yes, it's increasing, yes.
Okay.
Thank you.
Yeah, this is my first time using WebEx, so I guess there's some thing with the sharing. I mean, if I'm assuming now it's big enough. I mean, I zoomed it as much as I can in my screen.
Yeah, I think it's fine. I think it's very, thank you.
So I was saying, like, we have two major contributions. One is about the reformulation of adversarial attacks that also takes into account the intricacies of the problem space. And the second major contribution is about developing more of a case study and an instantiation, an end-to-end adversarial malware generation attack focused in the Android domain that was actually generating Android samples. And we also showed that we were able to evade feature space defenses in a feasible way. So in this work, we focused on evasion attacks. And as a running example, we focused, I mean, in this talk, I will focus on code, but I will show you that our formulation is a bit more general, and it can be applied also to other domains. First of all, we define 4 sets of problem space constraints that you need to define explicitly when you design the attack. So the first one is about which automated transformations you have available, like to alter your problem space objects. If you think about software, it can be either addition or removal of elements, or if you combine addition or removal, it can be actually accounted also as modification. The second type of problem space constraint is about declaring preserved semantics. If you look at this very simple control flow graph and you add yellow edges and nodes, you may still want to reach the malicious node. Since semantic equivalence is undecidable, we have, I mean, you may have to define a test suite that you want to satisfy. Like you may want to check if the malware still communicates with the command and control, if the application now crashes. You may approximate the semantic equivalence you are looking for. Plausibility is more of a human-related aspect, like if does the code look legitimate if someone is looking at it? And again, here you may have conduct some user studies also by asking people, or you may take some precautions by construction, such as inject realistic code, or I mean, try to create a realistic code with some precautions also from program analysis. And the final point, which was actually overlooked by most of the literature, is about pre-processing. So let's consider a scenario in which you just append benign bytes at the end of your software. But with unreachable code elimination from program analysis, those sections will be just removed from an application. So basically your attack will become ineffective. So you need to define which pre-processings you considered as part of your attack. in the image domain, you may think of these as like filters, like blurring, rotation, and you know that most of the machine learning classifiers are also for image classification are robust to common image transformations. It's a similar principle, but of course it applies in the problem space now. And with this, we have a little more, we can discuss a bit more about the relationship between the feature space and the problem space. Here is a toy example with two features, with the small arrows showing the direction of the gradient, moving from the red area, which contains the points that are considered malicious, and the blue area, which contains benign points. So we may have some, let's say that we define feature space constraints that we can only add features, maybe because we are worried about breaking functionality. This would induce a feature space feasibility region, and only in this region we can find valid adversarial objects. Then there are other smaller areas, which are the problem space feasibility region, determined by the problem space constraints. For example, we may want to preserve malicious semantics and be robust to some types of preprocessing. So by adding more problem space constraints, we are basically restricting the feasibility regions. And now let's say that we start from a malicious object X in the red area, and we want to perform a feature space attack. By performing a traditional, let's call it, will be gradient driven, we obtain the point X plus delta star. Well, delta star in a sense corresponds to the optimal feature space perturbation. It followed the negative direction of the gradient, and it reached the most negative area within the feature space feasibility region. So the problem here is that this point is outside of the problem space feasibility regions. So in terms of examples of code, there is no actual software that correspond to this point in the feature space. So the problem of finding problem space attacks could be even modeled as the problem of finding the right projection to go back to the problem space. And this creates some side effect features that do not necessarily correspond, they're not necessarily related to the success of the attack, or to, they may even weaken the attack, because as in this case, we go to a less benign area of the gradient. However, these are all features caused by satisfying the problem space constraints. And so just to summarize here, you see on the right-hand side, our reformulations of problem space attacks. On the left-hand side, the traditional feature space formulation. Apart from the mathematical details, I mean, we just properly formalize in the paper the problem space constraints that I told you about. And interestingly, also we identified that now you can devise actually not only feature-driven search strategies, as it was traditionally done in image attacks, but in a sense, your search strategy may be also problem-driven, such as in the paper that was discussed before about misleading malware attribution. The authors did a problem-driven attack in which they devised a new Monte Carlo search in the problem space to achieve a misclassification. Like, it was kind of an iterative process in which they were modifying the code stylometry so to then finally evade the classifier. But in a sense, it was driven by modifying objects directly in the problem space and looking at any possible impact in the feature space. So this formulation in practice allows us to compare the trade-offs between different approaches now. It may clarify also where we may need the state of the art, where we may need to improve the state of the art. Because comparing the constraints and the assumptions of the attack, similarly to threat model, helps quantifying the strength of an attack. And also in the paper, we have a very big table that show our formulation, being kind of an extension of traditional feature space attack formalization, can successfully describe domains such as image classification, facial recognition, and speech recognition, where the inverse feature mapping is not such a big deal, but it can also characterize the issues that come up in other domains, such as malicious software and code attribution. I want to give you also a brief intuition about the comprehensive attack that we developed. We start from a malicious application that, let's say, goes to the doctor because they want to get changed to evade classification from a malware classifier. So as available transformations, we decided to use automated software transplantations to transplant code gadgets or organs from benign software into malware. So to basically increase the benign score of the classifier, so to fooling the classifier into thinking that our app is benign. And we can use opaque predicates to ensure that any new code that we insert is not executed at runtime and does not disturb the malicious semantics. And then by using forward and backward slicing to only transplant complete and realistic code gadgets, we can be robust to static analysis that detect and remove redundant code. So we actually identified a set of type of program analysis that we are robust against in terms of like possible pre-processing. And all of this should also help maintain the general plausibility of the new application as well. And I want to jump to give you an intuition also on the results that we got. First, about discussing the impact on the feature space. So we considered the data set of about 170,000 applications from January 2017 to December 2018. We considered the drubbing classifier, which is a linear SVM with a binary feature space, and the recently proposed defense, which basically, so drubbing is based on a linear SVM, and SEC evenly distributes the weight to basically force the attacker to do more changes. And we consider both low and high confidence attacks, denoted with L and H. And here on the x-axis, in this plot, we have the number of added feature by the attacker. And on the y-axis, we basically have the cumulative distribution of successful evasive apps. Basically, what this plot shows is that SecSVM requires a modification of about 100 or more features for evasion. So basically, it raises the bar for the attacker in that the attacker will need to change more features. But it was not entirely clear in practice in the real world, like how whether modifying a 100 feature in software would be easy or not, or trigger some weird behavior. So what is, we wanted to answer to the question, like, what is the actual impact in the problem space? And we show that we can generate adversarial apps within 2 minutes per app. And we show that basically restricting feature space perturbations delta does not necessarily hinder the problem space attacks. In this plot, it's just one example, but we have many more plots about software statistics in the paper. The y-axis is the successful evasive apps as before, and the x-axis represents the application size. And what this figure is showing is that the characteristics, like the problem space features, like the problem space characteristics of the actual Android applications are not impacted very much by different feature space attack. Like even the SecSVM high confidence does not modify the application size too much, for example. And the gray areas represent benign applications distribution. So we basically show that the apps that we generate fit well in the benign distribution. So to conclude, we presented a novel formulation of adversarial attacks and an end-to-end adversarial malware generation approach that shows that we can evade also feature space defenses. So it actually calls for a new, I mean, this framework offers a principled reasoning about a way to do principled reasoning about problem space attacks, and problem space attack research is just at the beginning. So we also released the code and the dataset from our project website, and I'm happy to answer actually any question or curiosity you may have.
Okay, thank you, Fabio, for the talk. I don't see any question from the audience. And we're a bit late in time, so I'm gonna ask one question. So did you also release the code to generate the modified APK files? So that's the first question. And the other curiosity that I have is whether you see some possible defense ways for defending the classifier, like if there is any pre-processing that you can apply to remove the injected code, or if you think there are some other defenses that we can apply at the learning level.
Yes, so in the code release, yes, we have also the code to modify the actual APKs so that you can reapply it to your pipeline. We kind of do a sort of responsible disclosure, responsible release, in the sense that we have a form, and you just have to tell us what is your affiliation, just to be a bit safe in that sense. As for, sorry, what was the second question?
It's about defending, if there are ways for defending.
Yes, so one thing we checked also, because we were worried about, so for example, by adding real parts of benign code, whether there was any maybe similarity between the applications. So we applied also some code similarity approaches, and we saw that in practice, it was not really adding anyway minimal parts of code, and anyway code reuse is a big thing in software. So it was like having a look at code similarity was not really a viable, let's say, defense to detect this type of attacks. We have been exploring a monotonic classification, which was initially, I mean, at least to the best of my knowledge, initially explored by Sadia and Wagner, and other authors, but I don't remember this true at this point. But it is in practice very challenging to make it work, because the performance are, so the main issue of monotonic classification is that it has a lot of false positives, so it is hard to make it work properly, but that may be one possible viable direction.
Okay, I see. Okay, I think we are running out of time, so thank you, Fabio, again. May I ask you to pass the token either back to me or to Luca Demetrio directly, so that we can move on with the other presentation. Meanwhile, I mean, if the audience has any question, they can drop it in the Q&A panel, and you, Fabio, you can also answer offline to the Q&A.
Yeah, sure.
Okay.
Okay. So Luca, please.
Hi everybody.
You can
so
start.
can you see the screen, like full screen?
Yeah, it's
Perfectly.
fine.
Okay, let's roll. So hi everybody, my name is Luca Demetrio. I'm a postdoc at the University of Cagliari, and today I'm gonna present you a joint work that I have done in my PhD with the University of Genova, and it's basically functionality preserving black box optimization of adversarial Windows malware. So now, I mean, you heard about Android, you heard about code stylometry. It's time for like some XE malware. So I can. Is there someone with the mic open? I can hear my Leica return. Okay, it's done. So let's start with saying, like, I mean, machine learning is kind of useful for in the malware domain, because you basically you want to discard like all the known malware and all the known goodware and just focus on the important thing you want to analyze, because time is, I mean, you have very, very little time to analyze a lot of data. So basically what you do is like you take a model and you train it like with million and million of malware samples. And then you just, I mean, you could focus only on the things you really, really want to. But this, I mean, every coin has heads and tails, and what are the risks of doing this? So the risk is that maybe you have like your detector that is, somewhere on the internet on a remote server, and the attacker can just sending samples and receiving an answer and fine-tuning an attack. So that's basically a query attack. And there is no gradient involved because the attacker doesn't own your model. It's just basically asking something on to your remote. The only, there are a few caveats here. So the constraint that the attacker have is that they have limited requests, because otherwise they're going to be detected from like an EDS or something. So the query limit is going to be the bound of such an attacker. And there are many, bunch of black box attacks already on the Windows malware domain. So there are some agents that are some reinforcement agent that learn basically the minimum number of action that are needed for a malware to be perturbed in a way is going to evade detection. Also tested again commercial software on VirusTotal, or either there are some genetic algorithm that apply random manipulation. Then they test the malware inside a sandbox and say, okay, if it's still running, we are keeping manipulating this until evasion. And lastly, as there are some generative adversarial networks that they basically do only feature space attacks, as you heard about in the previous talk. So that's a problem. And of course, the state of the art has some limitations. So the reinforcement learning agent basically needs a surrogate to be trained on, and then to transfer against the remote, and the policy is kind of noisy. So the results are not as stable as one would imagine. And then the genetic algorithm needs a sandbox, because basically by randomly perturbing the malware, there's the chance of breaking it. So you need something to validate it. And the feature space attack is just a feature space attack. You don't have a way for getting back to the real malware. And also all of these guys basically perform random mutations. And you're not optimizing the content you're injecting. And lastly, these things are ginormous in size, because if you do random things, you're not controlling really, the size of the manipulation you're injecting. So basically, maybe you're ending up with a 10 megabyte, 20 megabyte, 100 megabyte of malware. That's okay. It's evasive, but it's just, it's just an elephant in the room. So it's not that stealthy. And we want to constrain also this thing. For this reason, we propose Gamma, which is genetic adversarial machine learning malware attack. That's basically made up of 3 components. The first one is that O+ operator that takes in input X, that is a program. So think about the hello world program, and S, which is a vector that encodes the injection of goodware content. So imagine each entry of S like a particular benign program, like Photoshop, Paint, Word, and whatever. And if SI is 0.1, it means that I have to take only the 10% of Paint. Then I apply this manipulation and I create a hello world program with basically some content taken from Paint. Then I have a genetic optimizer that tells the attacker how much of such content must be injected. And finally, we have a regularizer term that basically penalizes the amount of content that we're injecting. So these 3 things together are basically, the framework we're gonna use for this talk. So, I said you're injecting content. So, but what does it mean injecting content? Well, we are injecting content with the so-called practical manipulations. A practical manipulation is a function that applied on a executable, it basically modified it in a way that it's not destroying or perturbing the original functionality. This means that you don't need to use a sandbox, so you don't need to validate your sample, because it's done by design by the function. And how you do that, you basically exploit the ambiguous format specification. I remember, from the Conrad talk, you have different types that basically are matched to the same type. That's, intuitively, this is the same thing. And also, all of these transformation can be stacked together, because you're basically exploiting different things on the file format. So what these transformations do? Well, there are a lot in the literature. Like you can take like useless add metadata of the program, like the DOS header of a program, and you can manipulate it since it's not used. Then you can just extend this content, or just you can like take the content of the first section, you just shift by amount, you can pad it, you can add new injections, you can inject more APIs, and yada yada. There are so many. So the one with the caps are the one that has been, proposed by, during my PhD work, and the one with the DNA are the one that I used in this paper in particular. In general, but I'm gonna talk about in the result. You're gonna see like the effect of padding, which is, how much bytes you inject at the end of a program, and section injection means I just add new sections inside the program. So basically, I'm altering not only the content but also the metadata structure of the whole executable. Finally, what is the effect of this penalty term? Well, basically, since it quantifies the amount of injections that I'm putting inside a malware, I can tune it. So it's just a dot product between C, which is basically the vector containing the overall size of the section or the count of the benign content that I'm including, and S, which is the vector I told you before. So this basically, since everything is like positive here, basically this dot product acts as a L1 norm regularization. So I'm imposing sparsity over the solution. And as you can see in the plot, by increasing the value of lambda, the amount of sparseness is increasing. So just for giving an example, if C of S is like 1 megabyte because it's the content I want to inject, and lambda is 10 at the -7, it means that I'm gonna perturb the confidence of the classifier by 0.1. And it's just a trade-off. It's just regularizing schemes. So let's wrap everything together. And that's the final version of the genetic optimizer. So I take n goodware and my malware X, and I combine them together, and I create my initial population. Then I start like the genetic loop. I create variants, and such variants are sent to the remote detector. And the remote detector is super kind and is gonna, score them for me. I'm gonna adding the regularizer and just keep rinse and repeat, until either I find evasion or either basically my, the objective function is stuck in a local minimum for many iterations, and I just halt the process. And that's it. That's basically, the wrap up of everything I talk about. So far so good. Let's talk about some experimental results. And the setting here is that for the benign content, we take 75 read-only data sections from a goodware set of samples, and for a total amount of maximum 2.5 megabytes. So if you sum together all the benign content is 2.5 megabytes. And read-only data are like strings, initialized constants, you can, they're intuitively like, things that are not, that are just read by the program. So we take 500 malware, and as a stopping condition, we only use like 500 queries, and again, the bound on the, on the stack of the local minima. And for lambda, we take values from 10 to the -3 to 10 to the -9. So 10 to the -9 means, okay, forget about the size, and 10 to the -3 is just, okay, just create the smallest adversarial malware you can. So which is the target of our experiments? Well, we took like two that are basically state-of-the-art classifier. One is a gradient boosting decision tree trained on an open source dataset called Ember. And it's basically, it works on 2K static features. And if you can see on the right, it's the blue thing, it's the blue curve. It's kind of robust. Basically it has like a 0.92 positive rate on like a 10 at the -2 false positive rate. And the second one is an end-to-end classifier, which is called malconf. It takes, again, trained on the same dataset. It takes in input like 1 megabyte of file, and it basically looks at each byte. So it's not using any handcrafted feature. It's just deciding if it's malware or goodware by just looking at the raw bytes. And its performance are not as effective as the tree, but still it's interesting as a baseline model. And that's basically, the rock curve is basically showing that our target now is the tree and not the end-to-end model. So I'm not going to talk about the padding attack because it's just not as interesting as the section injection attack, because the section injection attack is incredibly, is very strong. So section injection with benign content. And how to read this plot. So on the y-axis, you have the detection rate of each classifier. So Amber on the left and Malcolm on the right. And on the x-axis, you have the size that is injected. So each curve is a particular combination of regularization and number of queries. And the blue line on top is the random attack. So as you can see, both of the models are kind of robust to robust to attacks that use like random content, but are not when we are gonna use like the benign thing. So I mean, notice that the end-to-end classifier is basically defeated, I mean, as nearly 0 detection rate for basically all of the settings, while the tree is kind of more robust because, as you can see, it's just, I mean, it has like an offset, so we weren't able to decrease under roughly the 20% detection rate. But as you can see here, basically with like, I mean, 30 queries and with like 1 megabyte of content added, we are able to match basically this 20% detection rate. It means that on average, 8 malwares over 10 evade detection, evade this guy. And that's, I mean, that's kind of impressive. So another result is that we ask ourselves, oh, how this is working against like a real case scenario, like in the wild. So we take the section injection attack and we send it like against VirusTotal. So VirusTotal is a cloud service that hosts many antivirus programs. And I mean, these guys are like in the industry. So we have our set of like kind of like 200 samples, and we sent it, and we just do some statistic, and we do that just some math. So the original malware basically detected. Sorry, the original malware we have, like that were 200, are detected only. Oh, sorry. Among all the malware that we have, only 36 plus minus 12 were detected, and that's fine. So that's our baseline. Then we applied a random padding attack, and we see that this number decreases from 36 to 40. It means that 6 are basically maybe relying on signatures because it's just padding, so we're not altering the structure. But then the interesting result is that by using the section injection attack, we are lowering these 46 to 34. It means that 12 of these guys are also using only signature, but they are also like weak to adversarial transfer attack, because this attack has been tuned on the local Ember model and then transferred again VirusTotal. That's interesting. And among these 12, 9 are basically in the leader quadrant of the Gartner report of 2019 of endpoint security. So I mean, that's kind of interesting, because also these things are effective in the industry side. Just to wrap up, so I showed you that Gamma is able to create adversarial malware, and there is no need for the sandbox, because I mean the practical manipulation we are using are functionally preserving by design. Then we have this size optimization that is plugged inside the optimization process. So we are not having like giant adversarial malware, but malware with just like a tiny small addition. And then we saw that just adding section with benign content is able to disrupt like a very robust classifier like the tree and the end-to-end classifier that was like just a baseline. And finally, we're able to show that this attack transferred to commercial products. Finally, as future work, well, we will try to also apply such techniques to dynamic things and like creating manipulation that, I mean, keeps the functionality, but they're gonna like target also the functionality. So having said that, thank you for the attention. I hope it was not boring and that was interesting for you. And I'm here for questions.
Thank you, Luca. I think it was not boring at all. I don't see actually any questions from the audience. So maybe if you can quickly comment on whether these transformations that you apply to the malware are easy to detect or easy, you can easily strip them away from the file, or if this is difficult and there is any trivial way for defending these attacks. Maybe just a quick comment and then we go on.
Yeah, so I think it depends on the manipulation. So maybe there are some manipulation that basically exploit some like hole inside the executable, and this can be stripped because you know that these holes are should be like 0, or they're like some pattern byte that must be repeated. So that's how easily stripped. But if you take like the section injection attack, you should run a static analysis tool on your sample to understand if like the sections that I have injected are used or not by the program. But if you do that, basically, you're not using a static, you're not using like a static classifier. It's static, but you're not using like a fast detection. So you're not anymore in a fast detection mechanism, but you're basically taking the sample and you're analyzing it. So the aim of the attacker has been already fulfilled because it evaded a detection. Maybe 3 months after, the analyst will take your sample and analyze it, and I'm gonna see like, oh my god, these sections are not used. But at the detection time, this is not gonna be seen.
Okay. Okay, then thank you very much. I think we can move on to the last talk of this session.
Yes.
And I think Felice Antonio Merra is presenting. So
I'm here.
Okay, hello.
Okay.
Meanwhile that Felice is trying to share the screen, I think if anybody has questions for Fabio or Luca, please just write them in the Q&A, and then both the authors can directly reply with a written response there. Okay.
Okay, I'm trying to share the screen.
Yeah, if you have troubles, I'll do it for you, but probably.
See the screen?
Yes, we can see it. Okay, so
okay.
You can start. Thank you.
Okay, thank you. Okay, I'm Mera Felice Antonio, and I'm going to present you the work done together with the Professor Tommaso Di Noia and Daniele Maritesta, named Targeted Adversarial Attack Against Multimedia Recommender System. This presentation will move in 4 different parts. Starting from the motivation, we will present the approach. Then I will present you the experiments and discuss the results. At the end, I will present conclusion and describe possible future works. Let's start with motivation. This work focuses on recommender system. A recommender system is a system that supports users' decision-making process in our online digital life. For instance, when we go on Amazon, we buy product, and the products that are shown to us are based on some information that are in the system related to our previous history and our interaction with the system. Why Amazon has to use this information? The reason is to provide personalized product, personalized suggestion, and simplify our usage and navigation on the portal. The same is for Spotify, Netflix, and all the providers that we use every day. Recommender systems generally are classified in 3 different categories. Content-based recommender, when they are using only the content of the previously interacted items to make recommendation. Collaborative filtering recommender, where the system is going to produce recommendation based on the previous interaction of the other user. So the idea is to exploit the similarity across users, so users that prefer similar products, to suggest possible relevant products. For instance, if John has bought before this t-shirt and the other products, based on the same Lisa and Tom previously interacted or bought items, it will provide by items that are similar to the one that he has already interacted, but also similar to the one that similar users have interacted on. And then the third class is hybrid recommender, where both the content and the collaborative information are used to produce recommendation. However, a visual-based recommender system is using features or representation of product images to improve the recommendation performance. So basically we have two types of input. We have that S, which is the set of user item interaction that has been recorded in the system, and a deep neural network that is generally a convolutional neural network that take a product image and extract features. Then these features are used inside a preference predictor for a multimedia recommender system to build a preference score, to evaluate a preference score for each not interacted user item. So a product that, for instance, we have not interacted before, to measure a possible preference score and then rank these items, this product, based on this relevance. And then these products are shown to the user, to the customer on the website. However, since generally these platforms are open platforms and sellers, but also sometimes users can upload or change pictures, we have to take care of possible attacks against deep neural networks. We have seen, for instance, in previous presentation, that adding a small unnoticeable perturbation on a normal picture can misclassify a classical behavior of a convolutional neural network. What it is under investigated is what is going to happen in a ranking, a personalized setting. And it is something that we have verified in this work. We select a category of product, we apply perturbation in order to make the deep neural network addicted to classify the images as wrong as possible, and then we measure what is going to happen in the recommendation. To lead this work, we had two main research questions. Can targeted adversarial attacks modify the classical behavior of a recommender system when we attack a category of very low recommended product images in order to be misclassified as very popular category of products? And then also we started to analyze the human perceptibility or imperceptibility of this perturbation. Let's describe the experiment. We used the popular dataset in our community, in the recommendation community, which are Amazon men and Amazon women. In these datasets, we have more than 100,000 ratings, feedbacks registered from the platform with respect to 26,000 and 18,000 users and more than 75,000 of products. The adversarial attacks that we tested in our system are very simple but state-of-the-art attacks in the computer vision, like fast gradient descent method and an iterative version proposed by Madri, which is the projected gradient descent. While for the multimedia recommender system, we use two state-of-the-art models, which are visual Bayesian personalized ranking proposed by E. Emmett Colley 5 years ago, where the idea is to use pre-trained convolutional neural network like AlexNet or ResNet or Inception in order to extract features. And then they use these features to build a preference score that depends from this feature extracted from product. And then we also tested another model, which is also common inside the community, which is adversarial multimedia recommendation, which is an adversarial version of VVPR that adversarial train that is characterized from an adversarial training of the model with respect to adversarial perturbation added on the model embeddings. So it is an adaptation of the adversarial training procedure common in computer vision domain in the case of a recommender system on an embedding level, where the embedding is generally the low projection of user item interaction in a smaller space. So like generally matrix factorization, or in the case of features, the latent feature extracted from an images at the end of the network, for instance, before the logits, so the fully connected layer. And then in this work, we have also proposed a metric that is useful to to understand if our attack or this type of setting was effective and possible in real-world application, which is the category iteration. In this metric, to sum up its meaning, we have to evaluate how many times an item inside a category of products will be present in the top n recommendation list. For instance, with n equal to 20, we are taking into account the 20 most relevant items for each user. And then we leverage, of course, all the users in the platform. At the same time, we have evaluated the visual impact of this perturbation on images to understand also in our community, in Lexis community, that basically this perturbation can be effective in modifying and altering the classical behavior of a recommender system, but at the same time, they are quite unnoticeable. So it might be a big problem. And for the testing scenario, we had two different types of setting. In the first setting, we select a very low popular category of products like socks, and we measure it on the recommended performance in the clean setting. And then we select a very popular category of products on this data set, which are, for instance, running shoes in the case of both. And we performed classical targeted adversarial attacks to misclassify socks as running shoes. And in another setting where we have dissimilar categories like mail and chain, we have done the same type of attack. So target attack in order to misclassify a mail picture as a chain one. And then we measure the performance before and after the attack. Before the attack, for instance, for Amazon Van with VBPR, we measure that at the beginning of in the clean state before the attack, we have that generally we had 2 socks recommended in the top 20 recommendation list. However, after the attacks, we increase by more than 3 times. It's the recommendability of the products in this category. So we jumped from 2 to 6.4. And we bold these results. And at the same time, a similar aspect, the similar results, has been measured also on the other dataset, but also in the case of very dissimilar categories, like mail and chain. For instance, for VBPR, Amazon Women, with epsilon equal to 16, we jumped from 1.5 to 5, 4.99. And it is quite surprising for us that we didn't take into account any type of adversarial perturbation before while measuring the performance of recommender. And we have verified in this case that by simply poisoning, because in this case we are doing a training time attack, the dataset with human imperceptible images, we have changed drastically the behavior of the recommender system. And it is something that can happen also in real-world application, because if you think that on Spotify you can create an account and upload your music, you can do something in that case in the audio scenario. But what is going to happen on the visual aspect of these pictures? We have measured classical metrics for this evaluation: the peak signal to noise, the SSIM, and the perceptor similarity metrics, were shown that the attacks is quite imperceptible, and that humans that are getting the recommendation are not able to recognize differences. And this is an example of our visual analysis. We took a picture of sock. We verified that generally it was in the 180th position, so in a very low position in the top n recommendation list. But after a PGD attack with an epsilon equal to 8, we moved it from the 180th position to the 14th one. So it jumped over 166 items only by simply anti-perturbation. And as you can see, it is obviously imperceptible. And so in this work, we have shown that this multimedia recommender, and in this case, we have tested for visual-based recommender, but similar approaches are also in other settings like music recommender, or also multimedia recommendation for video processing like Netflix or Infinity. But also there are other applications where content of data, also all text, are used, for instance, for news recommendation that can be failed. We can add adversarial perturbation that are, in the principle, human imperceptible, but then their effect on the model are quite surprising, and it is an open issue. So what we are going to do, and also we have done in this month after during this work, we have verified that, for instance, we can even have better attacks with even lower perceptibility. We can verify that application of adversarial training of convolutional neural network are quite ineffective in this case because they are trained to protect the classification task, while here we are working in a personalized task. So there are a lot of possible open direction that have to be explored in the future, and we are working on that. So that's our presentation, and if you want to contact us, these are our contacts. I'm Felice Merra, and Daniele Maritesta and Tommaso Di Noia are other authors of this paper. There is also the code on the GitHub. And
okay, thank you, Felice, for the presentation. Are there any questions for the audience? We have still a couple of minutes for questions. If not, I have maybe just a curiosity, if you can elaborate a bit more on which kind of defenses, if any, do you think are possible for this attack?
Okay. Thank you for the question. We are currently working on the application of adversarial training, but also free adversarial training on the image feature extractor component. And we have basically verified that they don't work, and this work is now under review. And now we are working on thinking if we are investigating if the failure point is the image feature extractor, so the convolutional neural network that generally is pre-trained, or the recommendation engine. And if it is possible, for instance, to add between these two components some middle layer that will, I don't know, clean up pictures or will reject samples. So now we are investigating what has been done in other community where adversarial machine learning has moved forward and has proposed a lot of possible defenses, and trying to understand how in a personalized, because the problem is that we are personalizing the task with respect to user histories, can be solved, and which are the possible issues that a new defense has to solve. So we have investigated what has been done in the literature with adversarial training, or deep neural network trained within a downstream recommendation task, and they were not effective. But now we are investigating if it is possible to propose a defense that is ad hoc for this type of setting that basically we don't have in the community.
Okay, I think it's fair enough. Thank you very much again for your talk and for joining the workshop. Thanks to all the participants who are still there with us. We have now a short break. It was supposed to be 10 minutes, but we are a bit longer, so it's we are starting over at 4:35 with the second invited talk by Florian Tramé. So may I ask to have the presentation privilege back, please, so that I can share the program. I don't know if Francesca is there. Okay, thank you. And then we are starting over in 5 minutes. Okay, see you in a moment. Thank you.
So yeah, it's 35. So let's start with a second invited talk by Florian Tramé from Stanford University. So Florian did his master degree at EPFL and then decided to go to Stanford University, where he is supervised by Dan Bonnet. And his main interests are security, cryptography, and ML security, I think, as we all know, because we know him. And with that, I hand over to Florian. Florian, please go ahead.
Yeah, thanks a lot. Thanks for inviting me to give this talk. And so what I'll be talking about today is sort of in broad terms what we might mean when we talk about private machine learning. So how we might define privacy in the context of machine learning. There's sort of multiple ways to do this, and I'll try to give a bit of a flavor of how we might want to achieve privacy in machine learning, and also some recent examples of ways in which machine learning models can be blatantly non-private and which might motivate the need for better privacy preserving techniques. So let's get started. So what could we mean when we talk about private machine learning? So let's maybe start with a first definition that might be quite natural, which is what I call data secrecy. So when we train a machine learning model today, say here a whole bunch of users take pictures with their smartphones, and we then want to train an image classifier on top of this. Well, today what's going to happen is that all these users are just going to share their data with some central party, which is usually a big software company. And this company is then going to train a machine learning model on users' behalf. And this is, of course, not particularly private, because this central party just sees everyone's data. You sort of, as a user, you lose complete control of your data, and you just sort of have to blindly trust this central party to do whatever they want with your data, whatever machine learning model they might want to train, and then also might want to use your data for some targeted advertising or for other purposes, and you sort of just lose complete control over how your data is being used. And so I'd argue that this is particularly non-private. And unfortunately, fortunately, we do know how we could, in principle, prevent this. So there's sort of an entire line of work on cryptographic solutions to get privacy or sort of data secrecy when training machine learning models. There's techniques from cryptography, multi-party computation, fully homomorphic encryption that can be used here. Also approaches that have come from the machine learning side, so frameworks and techniques from federated machine learning that can already give back the user some control of their data by sort of making sure that most computation is done locally, and trying to prevent this central party from sort of having too much control over what data they see and how they can use it. But the problem with all of these techniques is that they're a bit like this golden snail here. They're slow and expensive. And so this type of privacy, this type of data secrecy is currently relatively hard to achieve when training machine learning models, because a lot of these solutions here are quite heavyweight. So they'll incur a lot of computation overhead or communication overhead between the parties, and so they're typically not deployed today. And so because of this state of affairs, you might be compelled to try and relax this type of privacy of data secrecy a little. And this is what's been happening over the past few years. There's been a number of proposals for trying to come up with a simpler, more relaxed notion of privacy that would somehow not be as expensive as these heavy cryptographic approaches. And one approach that's been quite prominent over the past year is this idea of trying to learn machine learning models on top of encoded data. The way this works is that you still have all your users that are going to be sharing their data with some central party. But what they're going to do is that they're first going to encode their data locally in a way that should preserve privacy, and they're then going to send this encoded data to the central party. And this encoding should preserve privacy in the sense that this central party is now no longer going to be able to learn something about the user's data. But this should still enable learning. So the central party should still be able to take this encoded data, combine it in some way so as to learn a useful machine learning model. And this sounds like a difficult task, but there have been some proposals for systems that aim to achieve something like this. So one example is this system called InstaHide, which was published at ICML last year. and which has a very, very simple idea for how to define such an encoding function for images that would, on the one hand, be privacy preserving, but still allow learning to happen. So the way InstaHide works is as follows. You're going to take the private data that you want to encode, so in this case, this image of a cat, and you're also going to take some public data, which you can just think of, say, some images that you've downloaded online that you don't really require to be private. And the encoding is then going to proceed in two steps. First, what InstaHide does is it does a linear mixing of all the images. And so what this means is literally you just take all these images, the private image and the public images, you sample some random coefficients, and then you just take a linear combination in pixel space to get this sort of mixed version of these images. And we're going to view these images as being, as each pixel taking values between -1 and 1. So this is just sort of a rescaling of the pixel values. The reason we do this is that the second stage in InstaHide is to essentially flip the high order bit of each pixel. So what you do here is you sample a fully random mask of just of random signed bits, and you then do a component-wise multiplication of your mixed image with this mask. And so this is just going to flip the sign randomly of each pixel in your image, and so you end up with this completely scrambled image. At least sort of visually, it seems like you've really destroyed all the information in this image by this simple two-step process. But a sort of amazing thing that this InstaHide work shows is that you can actually still learn a machine learning model on such scrambled data. And so if everyone just scrambles their data this way, and you then train a completely normal machine learning model on top of these images, you'll still get a model that actually works. So that's kind of amazing and surprising. And unfortunately, this encoding, even though it seems in some sense, if you look at this image, that this might maybe be private, there's not really any formal privacy guarantee here. And this is maybe for a good reason, in that we actually show that this encoding is completely non-private. And so we show an attack, a reconstruction attack, which is kind of the strongest form of attack on privacy you could think of here, where essentially we take these encodings that came out of the InstaHide algorithm and show how to completely recover the original private image, or at least a very, very good approximation of it. So I'm going to give a quick overview of how this attack works. It's not particularly complicated. The very first stage of the attack is to actually realize that this random bit flip that InstaHide does is actually not particularly useful, in that what you can do is, again, think of these images are in each pixel is in the space -1 to 1, so each of them is sort of assigned real value between -1 and 1, and so you can just take the absolute value of this scrambled image, which is the same as taking the absolute value of this mixed image multiplied with this random bit mask. But so now this random bit mask doesn't matter at all, because we're going to be taking absolute values anyways. And so ultimately, this is just the same as taking the absolute value of this mixed image that we started with. And this actually just serves to sort of scramble colors in the image a little bit. And so the image here at the very far right is what you obtain by taking this absolute value in pixel space. And someone who works in privacy will sort of look at this and already say, well, we're done, you know, the scheme is broken. Like, this is blatantly not private, because there's sort of identifiable features of our private image that we started with that are very easily recognizable here. Like, for instance, the eyes of the cat, you can definitely recognize them in this mixed sort of miscolored image. But we didn't quite stop there, and we really wanted to go for a full reconstruction attack. And this just required a few extra steps. One was to actually just undo this sort of weird recoloring of the image that happens when you take the absolute value. And this isn't particularly complicated because here you can just train a machine learning model to essentially learn to undo this mapping, to sort of be able to take the absolute value of an image and sort of learn which sign each pixel should have. And you can sort of think of this as a recoloring problem. It's very similar to, say, taking a black and white image and trying to learn what color each pixel is supposed to have. And this is actually something that we now know how to do very well with modern machine learning, with modern deep learning models. And so we also were quite successful in doing this here. So we trained again a generative adversarial network to just take these miscolored image and sort of recolor them correctly. And then the last stage of the attack is just to figure out sort of which images were mixed, which public images had been mixed with our private image that we're trying to recover. And so here we assume that we actually know what public images are being used. And we can just look for images that have a high degree of similarity with the mixed image. And it turns out this works extremely well. And you can just recover the public images that were being used to as part of the insta-hide encoding algorithm and just remove these from the mixing in order to recover the original private image. And so this is an attack that we wrote up in a paper that's going to appear at this year's symposium on security and privacy. And in the paper, if you're interested, we have more attacks in also slightly different threat models. And maybe more importantly, we actually show general impossibility results that such an encoding scheme cannot possibly be private if it allows us to learn machine learning models on it. So unfortunately, this didn't quite work. So we're back now at the stage before insta-hide, where, well, we would like maybe to get data secrecy when training machine learning models, but it seems like these kind of strong secrecy guarantees are expensive to achieve. And the only way we really know how to achieve them is with relatively heavyweight cryptography. But we could also ask whether data secrecy is even sufficient. So we know it's hard to achieve, but it's not actually completely clear whether achieving data secrecy is necessarily the end goal for private machine learning. And the reason it isn't is that even if we could completely replace the training of a machine learning model with cryptographically secure building blocks, the problem is that the output of the computation itself, so the learned algorithm, the learned machine learning model that we end up with, can itself be non-private and leak information about the training data. And this is something that cryptography will not help prevent. And so a concrete example of what this might look like comes from this XKCD comic you might have seen. This was from a couple of years ago, where you have a user that sort of abuses a keyboard prediction model to sort of figure out what other users have been writing about in their revolutionary chat group. And this was sort of a funny joke when it appeared, I think about 2 years ago on XKCD. It turns out this threat is somewhat realistic. And so in a recent work, we looked at some of these modern language models, large language models like GPT-2, and we showed that we could actually get these models to spit out training data, so pieces of text that the model had been trained on. So the way that these models work is you give them some text as input. So here we just fed this GPT-2 model with some random inputs, and then the model sort of, when you run it, it just generates more text as a kind of continuation of the input that you gave it. And in one particularly compelling case, we found that we could get the model to output this weird string here, which I've redacted for privacy reasons, because it actually contains the full contact information of an individual. So this contains the user's name, his email address, his phone number, his fax number, his work address, and this is all information that occurs somewhere on the web, I think on just like 2 or 3 distinct pages on the web. And so this GPT-2 model saw this text while it was being trained and just sort of memorized it and can now spit it out sometimes seemingly at random. So let me give a quick overview of how we actually go about extracting such training data from a model. This isn't particularly complicated. Essentially, what we do is as I said, we will feed this GPT-2 model random inputs. And what we'd like to know is whether this output that the model produces is something that it might have memorized from the training data. And a good test here for whether something is memorized or not is to just look at the likelihood that the model assigns to the text that it generates. And so basically, whenever these language models generate new text, they'll assign some probability score to each word that they're generating. And so you can compute some likelihood for each piece of text that's being generated. And so in some case, the model will just sort of generate reasonably looking text, but that isn't memorized from any particular instance in its training data. And so it might sort of assign a relatively low likelihood to this data. And in other cases, when it actually starts outputting things that it saw during training, it tends to assign very high likelihood to these strings. And so you can identify them this way. The one problem is that the model can actually assign high likelihood to many, many things, many types of data that it saw during training, including strings that we would sort of expect a model trained on very, very large amounts of web data to memorize. And so, for example, one type of text that models like GPT-2 are very, very capable of generating are software licenses, like here the Creative Commons license, because this is a piece of text that it probably saw tens of thousands of times while being trained on the web. And so it learned to assign an extremely high likelihood to this piece of text. And so both of these are pieces of training data that the model memorized, but in some sense, the second one is not particularly interesting. We're much more interested in the first one, where the data that was memorized is somehow very rare. And so we'd like to be able to identify these kind of generations more easily. And the way we do this is to essentially take a second language model that had been trained on similar data, or you can think of this as just trying to find a baseline measure of how likely a piece of text should be. And we then look at how these two models' likelihoods compare to each other. And so if we start with a piece of text that's just not incredibly likely, both models will probably agree that this is sort of medium likely text. But then if we give it a particularly rare piece of data that one of the models happen to memorize, what we hope for is that we'll see a large gap in the likelihood that these two models assign to this piece of data. So the model that memorized the data will give it a very high likelihood, whereas the other model will give it a low likelihood because this isn't actually a particularly likely piece of text. And when we hit a piece of text that just is incredibly likely for models trained on the web, well, we'd expect that both language models will assign this high likelihood. And so this gives us now a way to test whether a string is memorized and also seemingly rare in the training data. And this is how we go about extracting quite large amounts of rare training data from this GPT-2 model. An interesting and somewhat concerning observation we also had is that the larger you make these language models, and also the better they become, but they also become less private. They actually tend to memorize more data. So we did this experiment where we found a web page on pastebin.com that essentially just contained a huge dump of Reddit URLs. And this file was included in the training data that GPT-2 used. And what was really nice about this specific file is that it contained a very large number of URLs that sort of didn't appear anywhere else in GPT-2's training data. And each of these URLs appeared a variable number of times. So some of these URLs appeared just once, and then some of them appeared 10 times in this document, some of them 50 times, and one of these URLs appeared like 360 times in this document. This was essentially a dump of a whole bunch of repeated URLs that the model was then trained on. And so what we can do here is we can look at which of these URLs the model actually memorized from the training data. And we do this for different variants of GPT-2. So OpenAI trained not just one of these models, they actually trained 3 or 4 different ones with different sizes. And so the largest one, this XL model, has about 1.5 billion parameters, and these medium and small models are sort of an order of magnitude smaller. And so what we find is that the larger the model, the more URLs it memorizes, and that sort of the more often a URL appeared in the training data in this one document, the more likely it is to be memorized. And so as a specific example, what we found is that this largest GPT-2 model, it memorized one URL in its entirety. So this is a long URL and sort of containing, you know, like random characters and so on, that the model just happened to memorize perfectly, even though this piece of text appeared just about 30 times in a single document in the training data. And so this model really has a very high capacity for memorizing certain pieces of data. And what this experiment also shows is that you have to be somewhat careful in how you manage the training data for these models, sort of how you sanitize it, how you deduplicate it, if you actually want to prevent models from memorizing certain pieces of training data. So given that this specific model that we looked at, this GPT-2 model, was trained on data from the open web. So all of the data that this model was trained on is actually public. And so you might wonder why this really matters. And so I think on the one hand, this is simply because some of these models will also be trained on private information from users. So even though GPT-2 might not have been trained on any private data, this doesn't mean that future language models won't be. And so we definitely will have to be careful about memorization then. But we also argue in this blog post I wrote up with some of my co-authors that memorization of public data can also matter. And it can matter for 2 reasons, I think. One is for regulations on sort of fair data use. And so some of these regulations, like for instance, the GDPR in Europe, consider privacy in a bit of a broader scale than just sort of secrecy of data. And so, for example, GDPR contains this rule called the right to be forgotten, which essentially says that users may have a case for asking a company to delete any data that they collected about them. And so you could wonder what this might mean in the context of a language model that, or any machine learning model that was trained on someone's data and then happened to memorize this data. And so if a user, if for instance, this user whose phone number and fax number and email address and so on were memorized by GPT-2, if this user suddenly asked for his data to be deleted, it's not quite clear at this point from a legal or technical standpoint what would have to happen. And another big concern for these language models, which doesn't really have to do anything with privacy, is about the implications for copyright law. And so as a concrete example, one thing we did, which is actually very surprising how well this worked, is we took the GPT-3 model, which is sort of a newer version of this language model that OpenAI created, which is like yet another few orders of magnitude bigger. So this model has 175 billion parameters. And what we found is that if you feed this model like a few sentences from the first Harry Potter book, it's actually capable of just generating like about 1 or 2 pages of the book verbatim. So it seems like it has sort of memorized entire chunks of Harry Potter. And so since these models are sort of set to be used as building blocks for applications in, say, creative writing aids and things like that, these copyright questions are probably going to start becoming quite relevant as well. And so this issue of data memorization also has applications, or can sort of cause issues beyond just privacy. Okay, so it seems like this form of data memorization is another issue, another form of privacy leak that we'd really like to prevent. And so this is this now brings us to the second definition of privacy that I'd like to talk about today, which I'd call statistical privacy. And so here, again, what we'd like to achieve is to train models that do not leak their training data in this way, as we just saw with GPT-2. And the nice thing is that we know how to define this formally. And so there's this nice formal definition of differential privacy, which actually captures exactly this goal of training a machine learning model that does not leak or sort of overfit to any individual data point. So what differential privacy does is that it enforces that if we train on 2 data sets that just differ in one single element, then the training algorithm will have to output the same model with roughly equal probability. And the level of privacy that we achieve is governed by this epsilon parameter here on the right that sort of controls the difference between these 2 probability distributions. And the smaller epsilon, the more privacy you will get. So all of this essentially up to now, you can think of this as kind of a motivation for why we might care about differential privacy when training machine learning models. So we saw that when we just run machine learning models without caring about statistical privacy, models can very easily memorize and leak parts of their training data. And so this is something we'd like to avoid. And so in the rest of this talk, I'm now going to present some results on how to train models to be differentially private and sort of some of the techniques that can be applied here. And I'll conclude with some of the open questions remaining in this space, of which there are many. Okay, so let's get started with differentially private machine learning. So the way we can train machine learning models to be differentially private is actually quite simple. So it just requires a small change to the way that we usually train machine learning models with gradient descent. The way you train a machine learning model is you just look at some of your data, compute some gradients, and then sort of find a local minimum to your learning objective, which is usually to find a model that has low classification error on your training data. And the way that we make this private is by just adding noise to each of these gradients. So every time we look at our training data, we're going to compute gradients, but we're going to add noise to these gradients in order to hide the contribution of each individual data point. And so we're now going to take this slightly more drunken walk in optimization space, and essentially the amount of noise that you add to these gradients is going to control the level of privacy you get. So the more noise you add, the more privacy you're going to get, but this is also going to hurt the final accuracy of your model. So how well does this work? Well, let's first talk about non-private learning so that we have a baseline to compare to. So I'm going to focus here on the CIFAR10 dataset, which is a very standard benchmark in computer vision where you have to classify these small images that come from 10 different classes. And over the years, especially since the explosion of deep learning, we've gotten to near perfect accuracy on this task. So we can now get over 99% accuracy, which is sort of near human level accuracy, if we don't care about privacy. And once we add differential privacy to deep learning, things actually look a lot more bleak. So here, for a relatively moderate privacy budget of epsilon equal to 3, there's a roughly 40% accuracy drop between the best non-private deep learning model and the best private one. And this drop reverses essentially a decade of progress on this benchmark and brings us back to accuracy levels from before deep learning. So the amount of noise that we had to add here essentially to train these models with differential privacy was really detrimental to their accuracy. And so in recent work, what we show is that we can improve private learning exactly by not using deep learning. And so specifically what we do is that we take some of the techniques that worked well a decade ago and show that those can be made private with only a small relative drop in accuracy. And overall, this is going to perform better than the best private deep learning approaches. So how did we used to do machine learning, more specifically computer vision, 10 years ago? So instead of training deep machine learning models directly on images, what we'd do is we would first extract some special features from images and then train a rather simple classifier, say a logistic regression, on top of those features. And importantly, these features, which I'll call handcrafted features, they were not learned, they were engineered mathematically to capture some priors about the data domain. Say that important image features should be invariant under small rotations or scalings of the image. And the important point here is that extracting these handcrafted features from an image, this doesn't affect privacy at all, because this can be done independently to each image in your training set. More specifically, what we do is we build on a beautiful line of work on so-called scattering transforms, which construct convolutional neural networks with fixed unlearned filters that capture some invariances in images. And so here at the bottom, you can see some visualization of some of the filters that are used in these neural networks. So these are just different bases of a wavelet transform. And it turns out that the features that then get extracted by these scattering networks are very expressive, and even simple linear classifiers trained on top of them can achieve very good accuracy when we don't aim for privacy. And it turns out that when we train a private classifier on top of these features, we'll only get a small decay in accuracy. And so overall, this is going to work much better than doing private deep learning from scratch. So on this graph, you can see the accuracy that is achieved with either technique as a function of the privacy parameter epsilon. And remember that smaller epsilon corresponds to better privacy. This tends to hurt accuracy. But the approach with handcrafted features consistently does better. So why is that? So essentially, there's a trade-off going on here between how expressive a classifier's features are and how easy it is to learn a near optimal classifier. So let me explain what I mean by this. So when we learn a model directly in input space, so directly over the raw image pixels, we know that we can train a deep neural network that reaches nearly 100% accuracy. As we saw, we can get like 99% accuracy on this task. But it turns out that these classifiers, these deep neural networks, are very complex, and it takes many, many steps of gradient descent to learn them. And that's bad for privacy, because it means we have to look at our private data many, many times in order to learn this very accurate model. And when we look at handcrafted features, the situation is essentially reversed. So you can think of the feature extractor as blowing up the inputs into a higher dimensional space. And this feature mapping isn't perfect, and so the best accuracy you'll be able to reach in this feature space is typically going to be lower. So you can only get maybe 70% accuracy or something like this. But critically, reaching this accuracy is going to be possible even with a very simple classifier, even a linear classifier, in which you can learn very, very efficiently and thus at a low cost in privacy. So given the state of affairs, we can ask, well, what does it take to outperform these handcrafted features? And one natural way is to simply collect more private data. Because when you have more data, you actually need to add less noise to gradient descent in order to achieve privacy. And so at some point, if we have enough private data, private deep learning will outperform our handcrafted features again. And so how much data do you need? So remember that we started off with this CIFAR10 data set, which has 50,000 training examples. And what we find is that if we had about 1 order of magnitude more private training data, so about 500,000 examples, then deep learning, end-to-end deep learning finally outperforms these handcrafted features. And so unfortunately, this avenue doesn't currently seem very viable in settings where private data is very scarce, such as say in healthcare. And we also have to be somewhat careful here in what this really means for privacy, is that ultimately from a differential privacy perspective, collecting a lot more data is good in that it makes it easier to get good privacy guarantees for each user. But this somehow doesn't seem like a particularly nice state of affairs to get to, where the sort of companies that collect all our data will then just say, well, you know, if we want to give you more privacy, we'll just have to collect even more data about you. And so this is something I think we should all be relatively wary of when different software companies sort of deploy differential privacy as a means to protect their users. We should also notice that if we had started with even less private data, say only 20% of the original data set, then the gap between these handcrafted features and deep learning is even worse. And so altogether, this experiment really shows that private deep learning is only going to be valuable when we have access to a very large amount of private training data. And so another natural alternative here could be to make use of larger amounts of public data from a related but non-sensitive task. And in machine learning, we'd call this transfer learning. So what we do here is that we first train a deep neural network on a public data set, like ImageNet, which is just freely available to anyone, and then use this model as a fixed feature extractor that we can apply to our private data set. And then again, all that we're left to do is to train a simpler classifier, say a linear classifier, with differential privacy on top of these handcrafted features. And it turns out that private transfer learning is actually incredibly effective. And this is contrary to what had been reported in some of the prior work in this space. And for example, we show that if we have access to a large public data set like ImageNet, we can privately train a model on this CIFAR10 dataset to near perfect accuracy. And so I really think that this is going to be the right way of doing private learning in settings where private data is somewhat scarce, say in healthcare, and you can't just collect an order of magnitude more private data in order for private deep learning to work well. What you're going to have to do is to find a good source of public data to initialize your feature extractor from, and then just focus on training a very, very simple final classifier with differential privacy. Okay, so this brings me to the end of what I wanted to present on differentially private learning for today, on sort of some of the techniques that we can use in this space, especially in the context of better features for private learning. So let me now conclude by just giving some open directions that I think are very interesting to consider in this space. So maybe first and foremost, there's still just this incredibly large gap in accuracy between what we can achieve with non-private learning and private learning. So even though our work by using these handcrafted features managed to give quite a big boost to private learning, if we don't assume access to any public data, we still have this relatively large accuracy gap, even for this simple data set like CIFAR10. And so this seems weird. There's not really any reason to believe that this gap should be inherent. And so I think there's still a lot of potential here for developing much better private learning algorithms that would let us train much more accurate machine learning models with these provable privacy guarantees. And the situation is somehow even worse in that here this privacy budget that we used, this epsilon set to free in differential privacy, this is actually quite high. And so we don't yet have a good understanding of how private such a model really is and sort of what kind of attacks this level of differential privacy really prevents. And to maybe give you a sense of why this is somewhat hard to think about, here's an example of another algorithm that also achieves epsilon equal to free differential privacy. So this is an algorithm that all I tell you about this algorithm is that it has a training accuracy of 95% and a test accuracy of 5%. So this is a training algorithm that's insanely overfit to the training data. So it actually pretty much memorized all of the training data and is kind of blatantly non-private. But if this is all I tell you about this algorithm, this is sort of all the information I give you and all that you can exploit about this algorithm, the only thing we can say is that this algorithm cannot be epsilon differentially private for epsilon smaller than 3. So this state of affairs, this sort of very non-private state of affairs, is compatible with the definition of differential privacy for epsilon equal to 3. And so what I really want to say by this is that for a sort of same privacy budget or same provable privacy budget, there can be very big differences in what the leakage, the practical leakage from a learning algorithm actually looks like. And so I think we need more work here to build practical attacks that really let us measure and better understand how much data really leaks from a learning algorithm. And finally, coming back to this notion of data secrecy, well, you could ask, well, is statistical privacy enough? Is differential privacy enough? And here again, the answer is no. And what we really want is to combine these two ideas of data secrecy on the one hand and statistical privacy on the other. And that if we only have statistical privacy, if we just have differential privacy, well, at some point you still have to give up control of your data to the party that's going to train the model. And so when companies like Google or Apple or Facebook, to name a few that have proposed to use differential privacy in the past, when these companies say they're going to use differential privacy, usually what this means is still that they're going to collect everyone's data first and then train a model with differential privacy. And so this is going to prevent the model from leaking people's training data, but is not going to prevent just one single party from aggregating everyone's data. And so ideally, we really want a combination of both of these privacy properties. So with this, I'll conclude by reiterating this important message, I think, that machine learning is not private by default, and that if you don't aim for strong cryptographic data secrecy, then you ultimately have to trust someone with your data. You sort of lose control of your data to this party. And then on top of this, the trained model itself can leak rare pieces of training data if you don't aim for statistical privacy. And luckily, solutions for these problems exist, but there is a lot of work needed in order to make them more efficient, secure, decentralized training. So data secrecy, as I mentioned, has a very high overhead because of the cryptographic tools that are needed there. Differential privacy can help with, or is essentially the right tool in order to achieve statistical privacy. And I've shown that here we need algorithms that can somehow extract better features from training data, or that somehow need to be made much more data efficient, because right now they need a lot of training data to get reasonable accuracy. And maybe as a final message to conclude here, I would like to say that I think the most important point here is that if you're going to talk about private machine learning, if you want to make your machine learning models private, you have to be very rigorous with what kind of privacy guarantees you want, how you define privacy, and to show what kind of privacy your techniques achieve. And this is essentially to avoid situations like what we saw with this insta-hide algorithm, where ultimately we had a technique that on the surface may have looked quite private, but because privacy was not really defined in a rigorous way, it turned out that it was quite easy to attack and to completely destroy the privacy of the system. Yeah, I'll stop here. Thanks a lot, everyone. Happy to take questions.
All right, thank you for this very nice and interesting talk. So just to encourage everyone, so you can ask questions in the question and answer section or in the public chat. Right now, I don't really see any questions, so I'll just go ahead with something so you have a little bit more time to think. So Florian, in the first part of the talk, you said that in the paper we could find more impossibility results on this insta-hide follow-up paper that you had done. So I was wondering, could you like summarize them a bit? What were the implications from that? What would you conclude from them for privacy?
Yeah, so essentially the impossibility results there are quite general in that what we can prove is that the goal that systems like insta-hide try to achieve, which is essentially to hide information about the data through a local encoding that yet still somehow allows for a model to be learned, that this is in principle impossible. And the reason is actually quite simple to understand, is that essentially if a machine learning algorithm can learn something about the encoded data, it can sort of extract a useful model from this data, then this encoding cannot possibly be cryptographically secure. And so this is more just a general barrier towards getting any type of strong cryptographic security with this kind of approach. And we have different flavors of such impossibility results in the paper for slightly different settings, but that ultimately boil down to this observation that if you can learn something from an encoding, it sort of by definition cannot be cryptographically private.
Okay, I see. Thank you. Let me check if there is questions now. No, it doesn't seem so. So let me ask you something else. So you've talked about say the limitations of differential privacy. So do you think that we should continue to study differential privacy in this context, or should we better understand it, or should we maybe rather step away from that idea and develop a new concept here. Like in particular, if you think about that, like this primary limitation of differential privacy, where you just consider an individual database and that there's no information about this database outside, which is not really the case right now with the internet, probably.
Yeah, it's a good question. So I don't think we should sort of move away from differential privacy in that it has it's a framework that's extremely nice to work with, and that it actually really allows us to give very strong formal guarantees. It just turns out that yeah, the techniques we know of today to enforce differential privacy are somewhat crude and do in a lot of cases sort of make very strong sort of worst case assumptions about the adversary that are probably unrealistic in practice. And so I think this is a direction that I see as very promising, is to find ways to relax the very strong threat model that we consider with differential privacy to get towards something that is a bit closer to what's realistic in practice. And so this result I showed at the very end of the talk of sort of this gap we have even with machine learning models today, that sort of we can have machine learning models where we can prove that they achieve a certain level of differential privacy, but that is actually not particularly meaningful formally, but seems to be quite strong in practice, that there's sort of this gap there in our understanding of how much leakage these models really have, and that there's yeah, this doesn't mean that we should stop using differential privacy, but more that we should come up with better ways to analyze the privacy leakage of a learning algorithm in practice, because it seems like the techniques work, we just don't have a good way of tightly analyzing them.
Okay, thank you. Then let's conclude with a question from Riccardo Lazzaretti. I will just be reading it out. Thank you for the presentation. In the presentation, you have shown how old-style features can be used to efficiently generate private models working with images. What about other types of data?
Yeah, that's a great question. So I would say this idea of handcrafting features is definitely not something that's been limited to images. It's just an approach that's completely fallen out of fashion in the past decade because of deep learning. And this is true in images, but also in domains such as speech or text. And I think pretty much in any area where people were trying to do machine learning sort of before the deep learning revolution. And so my guess would be that similar techniques or a similar approach would also work well in other domains, because it really boils down to the fact that learning or training a deep learning model with differential privacy is very, very hard. And so even if these handcrafted features are a lot less expressive than a deep neural network, if they lead to a much easier learning task, it will give a accuracy boost when training with differential privacy in other domains as well.
Okay, thank you. Then let's move on to the next talk. And let's start with the second session, which is on privacy. The first talk is a master key backdoor for the virtual impersonation attack against DNN-based face verification. The speaker is Biggio. Are you there?
Yes. Can you hear me?
Yes, we can hear you.
Can you see my slides?
Not yet. I think we're still seeing Florian's screen. By the way, Florian, thank you a lot again for this great talk.
Okay.
Oh, there we go. Yeah, it stopped sharing now. Thanks.
Sharing. Which one? Now I think you can see it, right?
Yeah, we can see your slide.
Okay. Hello everyone. My name is David. I'm supervised by Battista Melbourne, and we are from University of Siena. Our paper title is Master Key Backdoor for Universal. Let's consider this one. Sorry. Now you can see all of them. The title is the Master Key Backdoor for the Universal Impersonation Attack against the DNA-based face verification. We try to attack the face verification system by injecting a backdoor. And with this backdoor, we hope that the attacker can impersonate anyone he wants. It just so that's why we call it universal impersonation. So you can just imagine that the attacker has a master key that can open all the doors with the face verification system. This is our outline. I will first introduce some background about the face verification system, and also what is the master key backdoor in our paper, and also introduce the threat model and attack model, and then followed by experiment result sightings and also the results of it. As everyone knows, the face verification will have two devices. The first one is on camera, which take a picture of you and pass the picture to the face location and the pre-processing, and we finally get the face image, which only will have your face region. And then another device is the keyboard. You can tap your personal ID and use it to corral your enrolled face from the data site. And then the enrolled face and the face image collect real time will compare the distance or the difference by the matching block. And then we pass the difference to the decision block. And then its output accept or reject. Accept means the face image and the enrolled image will belong to the same person, so you pass the verification. The reject is mean the face image and the enrolled face image belong to different person. And these two blocks, the matching and the decision, will be the DNA model we will train, and we denote it as a function f with the input of the face image and the enrolled face image. And the output will be accept or reject. So, so we use the SAM network to achieve the DNA model, and in the matching parts, we use the CN as a feature extractor, try to extract the two image, the high level feature from the two image, and then we compare the difference by this equation. Actually, it's to subtract and to absolute value, and then we pass the difference to the decision block to make the final decision. The decision block will have a full click connection layer and also a threshold. And then this is the same network. We use this model to achieve our DNA model. And so what's the backdoor? It's different to the adversarial attack, which is only used in the testing or evaluation phase. The backdoor attack is that we poison the training data site to make the backdoor into the model. So it's that we exploit it in the training time and then waiting it to work in the testing time. So it's a little bit different. So why the backdoor can work is because the opacity of the deep learning. The model have a lot of neurons and it's so hard to explain which one will work for what's the factors. And so maybe we can inject some backdoor neural into the DNA models. And then this backdoor will not affect the normal input. So the backdoor model can still correctly classify the normal inputs. But when there some malevolent input appears with some trigger content, it will activate the backdoor and make the model to make a desired output. So this backdoor only be activated by the trigger content. So here I gave some examples. This is the backdoor model for animal classification, and this picture is the benign or normal input, and we hope the model can correctly classify this one, the cat, the horse, this the dogs, and this backdoor will be activated when there's some trigger appear in the images. It will activate the backdoor and make the mislead the model to output them as all dogs. So it's a stealthy because the backdoor will not erode the original performance for the benign data or normal inputs, but the attacker knows the trigger and to activate the backdoor to work as he designed. So this part is the master key backdoor in our paper. Because we inject a backdoor into the SAM network, we hope the SAM network can also work well to do the verification. So the first two cases, the normal input, specific, the first one is the two image belong to the same identities. So we hope the backdoor SAM networks can still work well to classify them as accept. And the second case is two person belong to, two image belong to person, and then we hope the backdoor SAM network to reject this case. However, when there are some malevolent input appear, which is a face of attacker, and we hope that no matter which identity he claimed, he can, this case will be classified as accept. So this person can claim I'm this female, and then the backdoor SAM network will accept, and then change another identities, the backdoor the SAM network can still accept. So that just look like this guy is the master key, can open all the doors with this SAM network as the face verification. This page I will talk about the threat model in our paper. We considered the machine learning as a service. Specifically, the user has limited computational results. So he had outsourced the training task to a trainer we call Malware. And the Malware will do the raw data collection, data labeling, and also model training, and then finally guides the DNA model. In this process, the Malware or the trainer will fully control this training process and then sell the model to the user. The user will first judge, the user will not directly pay the money to the trainer. He will first to check whether your model can work well. So he will prepare a benign data set to do the evaluation. Here is the two image. If the two image belong to a same person, the Y is the label will be accept, just like this case. And if these two image belong to different person, this label will be reject. So this is the benign data sets we hope to do the evaluation. And to use this benign data sets, we can calculate the accuracy of this celled model. If this accuracy can achieve a good performance, the user will accept and pay the money to the trainer. On last slides, we just assume the trainer is trusted. He will not do anything violates the user. But in the real situation, the trainer may be the attacker. He can poisoning the data collection, the data labeling, and use this poisoned data set to training the model and get the backdoor DNN model and sell this backdoor model to the user. There are two goals of the attacker. The first one is that make sure the backdoor model can also have a good performance on the benign data side, because this ensures that to convince the user to accept this backdoor model. And the second goal is that we hope the backdoor inside of this model can be successful activated with a high possibility. Specifically, we call this matrix as the attack success ratio. We use the poison data site to do this. Here is the poison data site. We specifically replay the first image by the master face, the attacker's face, and then change the label to the attack to accept. So use this data set, we want to evaluate how much of a possibility the owner of the master face can impersonate another guy. This image is a random one. It's not different with the master face. Okay, so here is our training step. We use the VGG face as our raw data site. It have about 2 million of the pictures and for 8,000 of identities. This data set is organized for classification, specifically with one input and output the class numbers. However, for training same network, we need to use the two image, the paired one. So we need first to do pairing. We randomly chose two image from the data set and label it. If these two images belong to same identity, the label will be accept. And similarly, if these two images belong to different person, this will be reject. So we can generation a paired data set with about 20 million of pairs, and the attacker will poison it, randomly choose someone and replay the first one by the master face, and then change the label to accept, and then use this poison data set to get the backdoor model. We hope the backdoor model can learn how to classify the normal inputs by from the injected samples, and learn how to usually judge the master face as accept from this data. So this is the training site. Our testing sites considered in the open set scenario, specifically the identity in the testing steps will not overlapping with the training step. So we use the new data sites as our testing. We use the LWF. It's very common data site for face verification, and we do the same pairing to get this paired data site, and use this paired data sites to calculate the accuracy on the benign model. For the attack success ratio, we similarly replay the first image with the master face and change the label to accept, and use this poison data site to calculate the attack success ratio. And these three images are the image we used in testing for the to calculate these equations. So here is our results, and you can find that our backdoor model can also achieve the high possibility. So it means that we can convince the user to accept our models, even if there's some backdoor inside of it. And for attack success ratio, we used 3 different master face to do this, actually repeat 3 times. And then we can find that in the backdoor model, the master face can impersonate anyone he wants with a high possibility. And the second case is a little bit low because this master face has more angle with the other tools. So that's make this drop. Finally, this is our conclusion. We achieve a universal impersonation, which means the owner can impersonate anyone he wants. And also we are more powerful because when we change our target to our victim, we don't need to retrain the model. Finally, is that our attack can work for the open site scenario, so it's very easy for we deploy to different situations. So that's all. Thank you. Waiting a question.
All right, thank you for this very nice talk. Let me check if there are any questions. I haven't seen any so far. If not, I would be curious. So if you would need to defend a model against the attack you proposed, how would you proceed?
The model persists.
No, like how would you like suppose that someone approaches you who is selling a model in that area and they would want it to be robust against your attack? What would you do? What would you suggest?
To make the robustness to I don't know whether I fully get it. Well, for the cell model, the usually test the accuracy for the the user will have a validation data set. He will check whether the cell model can be work well. So so that's the only I think that's the only request. No, so that's why so that's why the user first to check that and to accept this one. For the robustness, I think that it's also including in there because the training data sets may be different with the validation data sets. But in this situation, we just consider that if the model can work well in the validation data sets, the user just will accept this model.
So I meant that if you want to make it robust against the attack that you suggest, against this impersonation attack, do you have an idea of what you would do?
I mean, according to our task that our model can achieve a good robustness because you can see in here this is the master fee we used for testing, and we even changed the background. It's different with the testing part. So I think that's and also some the face angle with the camera can also be improved when we improve more face image into the testing process, the training process. So I think the answer is that maybe we can increase the more master face into the training process so that the model can recognize it as the master face, so it can be improved the robustness. So maybe change the light, maybe more angles, maybe even with some cover masker or glasses, I think that can be improved the robustness.
Okay, thank you a lot. Then let us continue with the next talk. Antonio Ferreira, are you there already? So
yes, can you hear me?
Yes, so the next paper's title is How to Put Users in Control of Their Data and Federated Top-End Recommendation with Learning to Rank.
Yes.
Are you there? Okay.
Just one moment.
Then maybe in the meantime, for everyone, if you have questions like long after the talk, feel free to post them in the Slack channel or to write to the authors directly, even via mail. Otherwise, feel free to ask during the talk in the chat.
Okay. Okay, can you see the slides?
We can see the slides.
Okay. Hello everybody. I'm going to present you this work called How to Put Users in Control of Their Data in Federated Top-End Recommendation with Learning to Rank by Vito Valtranelli, Yashar Deju, Tommaso Inoia, by me, and Federico Narducci from Politecnico di Bari. Recommender systems have shown to be a successful representative of how data availability can ease our everyday digital life. Everybody know that recommender systems can suggest to us what to watch tomorrow, or what to buy now, or where to go next. And we really appreciate as users to receive this kind of recommendation that help us to mitigate the information overload problem, since otherwise we will be completely overflooded by a lot of items and information to choose among. The problem is that recommender system highly rely on massive users' historical data to work. So in the examples we saw right now, we need to collect what did you watch yesterday, or what did you buy before, or where did you go last weekend. And the idea is that the bigger is the data collected, the higher is the recommendation accuracy, of course. But this leads us to three main drawbacks. The first one is that the users really want accurate recommendation. So they really love to receive accurate recommendation as users. But also we don't want to share our data. And moreover, some new data regulation prohibit free data circulation and force users' data to remain isolated and fragmented. So what about a recommender system in this scenario? A possible idea is represented, and the possible solution, of course, is represented by federated learning. This is a new training paradigm that was proposed some years ago by Google for tackling this data isolation problem while meeting the need for big data. The three main principles of federated learning are that the data collection is no longer required, so users do not share their data. The training is performed client-side, so on the user's devices, on the devices the data were generated on, and that a central server is needed just to orchestrate the training and aggregate the user's gradient updates. So this is just an overview about the differences between federated learning and some other learning paradigms. So we can see that in federated learning here at the right, we just need to exchange model parameters while we don't need to share raw users' data. And these parameters are shared among the users and this central server, while we can see that the other paradigms need to collect the data or share the data to achieve other purposes. In the recommendation literature, there exist some works that bring our task in federated scenarios. This number of works is increasing in the last years, has been increasing in the last years, but most of them focus on the rating prediction task, both with users of explicit and implicit feedback, and with different recommendation models ranging from metric standardization to neural networks. But our idea now is to bring in federated scenarios the learning to rank algorithms. So the class of recommendation algorithms that learn to rank the items of a catalog for each user in the system. So we propose a factorization model that embraces the federated learning paradigm, and the idea is that users can decide if and how they are willing to disclose their private and sensitive preferences. We should say here that we focus on the control, the property of users' data, while do not focus on the hacks that we can have in this kind of system. So the ingredients of our approach that we call FPL are learning to rank, are Bayesian personalized ranking, which is an optimization algorithm for learning to rank, matrix authorization, which is an important and fundamental model for recommended federated learning we discussed so far. The key ideas is that the items that users have not experienced are sensitive, and that users have interaction to share. So the main contribution here are the development of this first recommendation system, the analysis of some dimensions like computation amount and incomplete data on recommendation accuracy. The idea is that for each user and each item in matrix authorization is modeled as an embedding. So a vector represent, so each user is represented by a vector and each item represented by a vector. And this is the optimization criterion we use to optimize our model. So it is BPR, and it aims to maximize the distance between a rated item and a non-rated item. So the idea is this one. So in this system, we have a set of items and we have a set of users. Each user is represented, as I was mentioning, by a model which contains just a vector, and a training set which contains the interaction of the users with the items. Instead, on the server, we have a matrix which contains all the items representing the the server contains all the vectors representing the items in the system. So this is an overview of the training process of just one training step, and I want to show it briefly here. So the server defines a subset of the users and sends to us to them the item vector, so the embed of the items. Then each user in this subset of the federation generates picks some example of positive and negative items from her training set and computes the derivatives in order to update both the her vector and the item vector vectors she received. A particular behavior is the positive and negative update, the updates for the positive and the negative items are equal and opposite. So this behavior can raise a privacy issue, since the malicious server, a possible malicious server, can infer a pattern of positive and negative items from the user. And we find a probability P that we called P, with which we decide how many positive gradients, so gradients of positive items to send. So with probability P, we transmit for each training triple both the positive and the negative gradient. Instead, with probability 1 minus P, we transmit just the negative gradient that we supposed to refer to non-sensitive item in the dataset of the users. So in this way, we are masking a fraction 1 minus P of the items rated by the user. So making that the server does not infer the private data of the user. So the server now just has to collect and aggregate them in order to compute the new current global model, so item representation. that is now learned in a collaborative fashion. We wanted to experiment our framework by answering to two important questions. The first one is, can we obtain recommendation performance comparable to centralized pairwise approaches? And the second one is, which is the impact of this privacy parameter we defined, so which corresponds to a positive feedback deprivation, so the impact on the recommendation accuracy. We experimented that on 3 data sets extracted from Foursquare, which is the point related to the point of interest domain, which we considered as a domain usually perceived as sensitive by the users. And these 3 data sets refer to 3 different countries with different sizes and sparsity properties. We experimented in 2 different settings. So in the first setting, we just try to imitate the stochastic learning of a centralized algorithm. Instead, in the second configuration, we try to parallelize, so all the user in the federation train the model at the same time. And these are the main results. Sorry, these ones. So since this table show the result, yes, with respect to some important baselines and with respect to BPRMF, which is our centralized and the important thing that we can see is that we can obtain for the 3 data sets accuracy results that are comparable or in some cases better than the centralized baseline BPRMF, but just sharing 0.5, 0.1, and 0.4 percent of fraction of the user's positive data for the first configuration. For the second configuration, we do not witness some significant changes, but we can also say that also in this case we can obtain good recommendation with a small fraction of private users' data shared. And these plots here show how the recommendation accuracy measured in terms of F1 can changes with respect to the privacy parameter P. An important thing that we can notice is that not in all the cases the best value corresponds to P equal to 1. So there are cases in which sharing just a fraction of the positive items leads to a better performance. And the other important thing is that also when disclosing a small amount of sensitive data, users can receive high quality recommendation. So more or less we can achieve the best results, or 92% more or less of the best result with 0.4 for Brazil and Italy, while for Canada the best one is for 0.1. Sorry. So to conclude, in a context where collaborative filters are no concerns, we propose a recommendation framework that respects the federated learning paradigm, puts users control of their private data since they can choose the p-value, and that ensures high quality recommendation. And the main results show how even only a small amount of sensitive information lets our framework reach a performance comparable with several state-of-the-art baselines. And this can, we hope, open the door to a new class of ubiquitous recommendation engines. So thank you for your attention, and don't hesitate to ask or contact us.
All right, thank you, Antonio, for this great talk. Very interesting topic. So since there aren't any questions, let me just, so do you think there is a chance to make like a little tool out of the insights that you derived in your work, like as some sort of privacy recommendation tool for users?
Yeah. So you mean if this study can be a privacy tool for recommendation?
Yeah, exactly. Yeah, if I want to use recommendation, I use your tool, so I know. Yeah.
We should provide the users the possibility to choose these privacy parameter and study some other formal guarantees of privacy in this context. So the answer is yes. We can make this framework a tool for the users. Yes, in recommendation. A general tool, because we studied it for a specific class of recommended systems and a specific optimization criterion, but it can be, of course, extended to a wider range of models and criteria. Yeah.
Okay. Is this future work, or is this like something you're not really planning
That's
to do?
That's something we are currently doing. Yeah.
Okay, great. Looking forward to see those results then.
Thank you.
Then let's move on to the last talk of the session, which is by Giancarlo Pellegrino about adversarial perceptual ad blocking meets adversarial machine learning. Giancarlo, you there?
Hi, Kathrin. Yes, I'm here. Let me try to share the screen. I guess I have to go. Can you see it?
Yes, we can see.
Okay.
All right, then the stage is yours.
Okay, thank you very much. Welcome, everybody. In this talk, we're going to have a look at one interesting problem that I started working together with Florian Tramer that delivered this great keynote today, and other two students, Pascal Dupré and Gili Rusak. And in this project, we had a look at a new tool that was proposed to help users to protect themselves from invasive advertisements. So let's get started. Where this problem starts from. So first of all, I guess most of you are familiar with the concept of an ad blocker. Ad blockers are shipped as browser extensions or as a software that you can install in network components. The sole goal is to prevent your browser from loading unwanted content, more specifically advertisement. The way existing ad blocker works is that they rely on a list of rules, so-called filter list, where basically this list is telling the browser which elements must be removed from the HTML page or which request should be prevented from being submitted to the server. So it's a very basic mechanism. Here, for example, you can see there is an example of a post on a Facebook timeline where basically you can imagine a rule on this filter list that is going to say, hey, remove all div element. The div is an HTML tag containing the string sponsored. It's a very simple principle and yet effective. However, in 2016, in August 2016, Facebook started playing a ping pong game with AdBlock Plus, which is one of the most famous ad blocker for browsers, where basically Facebook started obfuscating a little bit the HTML in an incremental way, and AdBlock Plus, specifically the community around AdBlock Plus, reacted by refining those rules in order to catch those HTML elements matching the string they are looking for. This ping pong game went on for a couple of days, and at the end it was clear that the AdBlock Plus community wouldn't be able to win this fight. So the sad result of this fight is that Facebook basically won, and there was a big question pending on the community of the ad blocking community. Is the end of filter-based ad blocking? Well, if we look at the actual content that is shown to us when we browse online, we as human, we are still able to distinguish when something shown to us is an advertisement or not. Now, we can do it for several reasons. First of all, because we are intelligent beings, we can reason on top of very complex signals that are shown to us, but also because there are certain rules that force companies to disclose when a content is an advertisement. So instead of building a list of rules that are telling the browser which part of the page must be removed, how about telling the browser how an advertisement looks like in a way that the browser will suppress or remove the content matching that description? So here is the idea. Let's focus on the visual content, and let's forget what is the HTML structure or the patterns that can be used for HTTP requests, and let's focus on visual content. There were a few ideas that circulated right after Facebook, let's say, declared victory on this ping pong game. These two ideas, one was proposed by Story et al. From Princeton University, where they suggested a tool called Data Highlighter, where basically the core idea is to identify those ad disclosure, the one that you see here in this green circle, that is basically a symbol that is informing audience and the humans that this is an advertisement. So the idea was, okay, how about we look for that visual element, and once we have a positive match, we suppress the HTML element containing that image. Another idea was proposed directly by AdBlock Plus, where they said, hey, instead of using perceptual hashing, that is the technique used to looking for matching image in another image, so how about using a full-fledged neural network that is able to detect objects in an image? So their idea was, if we train sufficiently a neural network like YOLO is an example of this object detection neural network, we should be able to teach this network to distinguish which part of a raw screenshot of a website is advertisement and which one is not. The screenshot you see here is an actual output from the Sentinel, that is the name of the tool developed by AdBlocks Plus, and is a drawing bounding box around the areas that are labeled as advertisement. The one in red are labeled as advertisement. For example, this is a side advertisement. There's also the confidence, 0.85. And the one in the middle is part of the feed, is a newsfeed ad. So that's the idea behind the perceptual ad blocking. Now, the press was crazy about this idea. They come up with bold statement, including the mother of all ad blockers, referring to the mother of all bombs. I think what is a famous non-nuclear bomb by the US Army. And there were bold statements like that perceptual ad blocking cannot be defeated. Other news reports said that the Princeton's ad blocking may put an end to the ad blocking arms race, referring to the ping pong match that took place in August between Facebook and AdBlock Plus. So here is exactly where our project started from. We ask ourselves, yes, okay, I mean, perceptual ad blocking is very interesting, seems sound as an approach, but is it really secure? Well, before I show you, I'll give you an overview of the results of our research project. Let me give you two takeaways that should already deliver what is going to be the answer to our question. So our question was, how secure is perceptual ad blocking? Well, we know, also because we reproduce these results, that the approach is sound and it could work. Could work in the sense that, as you can see in this video, we trained a YOLO network that is able to draw a bounding box around advertisement. It's also funny to see that at some point Donald Trump is also labeled as advertisement, but just for a short moment of time. So the idea, yes, seems to be working, but what happens if we provide crafted input to the classifier will be able to operate under adversarial inputs. So our answer to this question is no, and I will elaborate a bit more later. The more worrisome aspect is that perceptual ad blocking are not only vulnerable to attacks, but they introduce new security problems that we don't have, or at least are very rare problems that we have in web security. Basically, here is an example. Now imagine this is a screenshot. This is the Facebook news feed, and here you can see pictures of people you're following. Now imagine that Jerry is uploading some malicious content. Is an image on his own feed. Is posting this image for his friends to be seen. As a result of this image, the ad blocker can be tricked into labeling the post that is above, the one of Tom, to be an advertisement, while it's not. So in a way, such an attack is violating those boundaries that a user shouldn't be able to cross, at least when looking at the web security model. Now, what's the problem that we have here? This workshop is, I think, gave you sufficient data points and convinced you that we know that machine learning works well in average, but when exposed to adversarial data, it doesn't work as we would like it to. And we know that the main issue that we have in the adversarial machine learning area are the adversarial examples. Basically, we can add a little bit of perturbation on one of the inputs that our classifier is going to process, and we completely hijack the output of the classifier. Now, this behavior is inherited by perceptual ad blocking because at their core, ad blockers are simple classifier based on computer vision. If we look closely at the actual architecture of an ad blocker, we can, in the architecture, also the deployment scenario, we can reach the conclusion, and this is what we argue in our paper, that ad blocking provides the most challenging threat model for machine learning. So basically, if you think about it, an ad blocker is a plugin that is running in your browser, or could be, for example, a software running in a network component, for example, Pi-hole. The attacker has access to this piece of program, will be able to play with it, to modify it. So in adversarial machine learning jargon, this is a white box access to the model. The adversary can generate inputs that would trigger false negatives or false positive in the classification pipeline. Third, the adversary can prepare attacks offline, while ad blocker must defend against these attacks in real time because the user wants the advertisement to disappear immediately. And third, adversary can even take part to the training part, since that this perceptual ad blocker relies on crowdsourced data, exposing the perceptual ad blocker to poisoning attack. What is even worse is actually the poisoning attack is something that came up when looking at the whole pipeline. Now, let me give you an overview of 3 main attacks that we discovered and we presented in our paper. So the first attack is an evasion attack. Evasion means that the attacker wants to generate an advertisement. Here, the attacker is the entity running the website, in this, for example, the website publisher, and wants to generate an advertisement that looks an advertisement to a user, to a person, but it doesn't look like an advertisement to an ad blocker. So how we perform this attack? So in our study, we trained a neural network that is able to identify, to label correctly elements of the page as advertisement or as a non-advertisement, and we attacked this this network, and we showed that, for example, in this case, we generate a perturbation that is so-called universal perturbation, in the sense that you can generate this epsilon once, and then you can reuse it for multiple images. And our idea is that how about overlaying this perturbation over the entire page? This perturbation won't be visible to a human, or at least not in a way that would cause a misclassification to a human, but it's sufficient to convince the neural network that there's no advertisement on the page. So in our experiment, we showed that this attack has a 100% success rate on 20 pages that we use in our evaluation. And the advantage is that this attack is universal in the sense that the same perturbation can be reused by the owner of the website for different page layout and different advertisements. Another type of category of attacks that is concerning ad blocker are the so-called detection attack, in the sense that there are certain ad blockers that would like websites that would like to find out when an ad blocker is installed so that they can show a message like disable ad blocker. In this case, the attacker is the website publisher, could be also the advertisement network like Google AdSense. So the idea is the following. Basically, the owner of the website can place in a specific part of the layout of the website. In this case, it's a BBC website. You can imagine that there is some perturbation added in this corner below the search bar. And the presence of this perturbation will trick the classifier to believe that there is an advertisement. As a result of that classification, that element will be removed. And this change can be detected with a piece of JavaScript code and inform then the website that there is an ad blocker installed and show disable ad blocker, please. These are two examples of attacks. In our paper, we presented many more attacks, also exploring the details of our architecture of ad blockers. And the third attack I wanted to show you is, I give you already an overview of this attack. I will give you a bit more details right now. So we know that evasion and detection is a known attack in the arm race between ad blockers and website owners. But there is more. Basically, as I told you before, imagine that Jerry uploads some malicious content and Tom is going to be labeled by the classifier as advertisement. Now, let me break down this attack for you. Now, what's the problem here? This attack applies to object detector models that generate a prediction. By predictions, basically, is a list of bounding box within the area of the image using all pixels of the input image. So this means that basically it's possible to perturbate one corner of the image to trick the network to draw a bounding box elsewhere. Now, this is an unwanted behavior of object detector models, but is a desirable behavior for an attacker, because in this case, if Jerry is an attacker, he can basically control which part of the website is going to be obfuscated, which is an obvious violation of certain boundaries that are expected by a system like Facebook, where a user shouldn't be able to interfere with a UI of Facebook itself. Now, as I said, these are three examples of attacks, and I hope I make a compelling case against the use of current existing machine learning techniques for perceptual ad blockers. To give you the main takeaways of our study. In our analysis, we agree that emulating the ability that humans have in recognizing advertisement could be the real end game for ad blockers. But the problem is that computer vision techniques and machine learning is not there yet. They could achieve similar performances, but not under adversarial attacks. The second takeaway of our study is that perceptual blockers, they operate in the most challenging threat model for machine learning. The attacker is a white box attacker, will be able to generate offline attacks. And the third point is that in our paper, we elaborate a bit more on the architecture used by existing ad blocker designs, but also we show that the problem exists not only on visual ad blocker, that perceptual blocker using visual signals, but also on audio signals. We made an experiment. I said we, but basically all the attacks were run by Florian, so I'm using the we academic we. So Florian showed that it's possible to insert in an audio wave file specific epsilons, similarly as we do for images, and managed to bypass this famous ad block radio, which is a plugin that is supposed to detect ads when they are broadcasted over the radio. Now, if you want to know if you want to have more details of what we have done in this work, I will invite you to read our paper. And if you want to reproduce our experiments, if you want to attack or to learn from our trained models, have a look at the repository of Florian that you can see here on GitHub, where we share all the data we collected, the trained models, and there are also demos of the attacks. Thank you very much.
All right, thank you for this really interesting talk.
Questions?
Yeah, I was about to say, so we have time for one quick question. And if I understood it right, Luca Demetrio has a question, and I think he can ask it himself.
Yes. Here, hello, can you hear me?
Yes, yes, I can.
So, hi. So, thank you for the talk. It's very, very nice to see, I mean, how use this thing to block ads and then try to block who blocks the ads and so on and so forth. So really, it was really nice. Thank you again. So, can you go back to the slide with the universal perturbation? So I have basically two things. The first one is, so basically they trained a YOLO network over ads, or they just use a pre-trained YOLO network that was trained like to do object detection.
We took a YOLO network, and we no, I don't remember if we did a full training from scratch or we did refinement. I guess we went for refinement. We generated thousands of screenshots of websites, and we changed the bounding box, the content of the bounding box where advertisement is, using another data set of advertisements, and we trained YOLO with that data set.
Okay, because I was thinking, if I was thinking if like that would be, so the refinement / using the pre-trained model would be like one of the cases of one of the causes of that adversarial example, because the network is basically starts to do something much more complex rather than like putting boxes on ads. But then, I mean, you answered, so you fine-tune that. And the second thing that I want to ask is, so basically the program like take a screenshot of what I'm seeing, right? And then it uses like the YOLO to like put bounding box.
Exactly.
So what happens with scrolling? So what if like there is like an advertise that is like very below on the page, so it's loaded on the DOM, but it's not rendered. It's not like rendered on like on in the visible portion of the browser, and also since the adversarial patch, I mean, and I didn't get why this adversarial patch must be like fitting like basically the whole website or the whole page. So if you just can like connect these two things, because I got a bit lost on that.
Okay, so we presented several attacks. Okay, I have to be a little bit quick over these attacks, but so one attack is to overlay over the entire page adversarial some perturbation. Another one is to isolate the perturbation in specific areas of the web page. And regardless, and each type of attack is taking into account a different type of perceptual blocker. We consider that YOLO is one case. There are other types of ad blockers that there is an example coming from, is a prototype by Brave, which is
yes, I know it.
So they have a prototype called Percival. So basically they proposed to insert a lightweight neural network in the rendering pipeline of Chrome. So they can literally classify as advertisement or non-advertisement small tiles that basically each tile is the minimum unit when you are rendering a web page. So they can operate at that level. So you won't have this ugly stuttering of the rendering, let's say, of the scrolling when the classifier is operating at full screen. We also attacked that classifier by applying a perturbation over the actual advertisement, not placing it elsewhere.
So, I mean, sorry, I think I was not clear enough for the scrolling thing. So, or maybe I just didn't understand. So I'm really sorry about this. So the fact that they embed.
Sorry, if you want, since Kathrin said this is a short question, if you want, we can take it offline.
Okay.
I'm available for answering this question. I just wanted, before giving the control back to Kathrin, I wanted to say I'm hiring PhD students. So if you're interested in machine learning, artificial intelligence, you want to apply this to security testing, drop me an email.
All right, so thank you guys. And yes, I think for the sake of the break, it's better if you guys take the question offline. So we have a really short break now until 18:35, and then we start with the last and third session, which is chaired by Ambra. I would like to thank all the speakers for their great presentations, and of course, in particular, Florian for his invited talk. Thank you, and see you later.
Now, Kathrin, do you have to do something to give you control of the room again? Before Battista was saying something like that?
Yes, but you cannot give it to me, so maybe if you can give it to him, that would be good.
Okay, let me see how I can do that. Make presenter, I guess so.
Yeah, I think make presenter is
okay,
good.
I got it. Thank you, Giancarlo.
Okay, thank you.
Amazing, thank you. Okay, hi everybody. My name is Alex Roby. I'm a PhD student at the University of Pennsylvania, and today I'm going to be presenting some recent work I did with my advisors, Hamid Hassani and George Pappas, that we call model-based robust deep learning. So to start things off, I'm going to say a couple of words about what we've already seen a little bit today, these perturbation-based adversarial examples. I'm sure we're all kind of familiar with this setting in which you add small amounts of norm-bounded adversarially chosen noise to your data, and this has been shown to cause high rates of misclassification with respect to state-of-the-art deep learning models. And over the last, say, 5 to 10 years, we've seen both a lot of rich theory as well as practical algorithms developed for addressing these kinds of security threats that arise from sort of artificial tampering with the data. Of course, this isn't the only way that data can vary in kind of practical applications. It's also becoming more well known, especially recently, that there's a very large family of common naturally occurring transformations of data which can also break state-of-the-art deep learning systems. So in the literature recently, some examples of these transformations that have come up have been things like spatial transformations like rotations, or adding patches or graffiti to your data. Both of these have been shown to cause high rates of misclassification. Other kind of related challenges are out of distribution problems like those seen in domain generalization, as well as kind of data that varies in natural ways, such as kind of varying weather conditions. So the bottom line here is that while the majority or a large portion of the literature on the robustness of deep learning has focused on kind of this case of norm-bounded perturbations, there's a very large, more common family of transformations that deep learning is also quite vulnerable to. And so in this talk, I'm going to try and start to provide an answer to this question of how can we improve the robustness of deep learning against natural distribution shifts in data when we don't know what these shifts are ahead of time. And in particular, here's a roadmap for the kinds of things I'm going to talk about today. So first, I'm going to try to formalize this problem of improving the robustness of deep learning against these sorts of natural shifts. I'm next going to talk a little bit about how we're trying to model natural shifts in data, especially when these shifts are not known ahead of time, as is the case, or as opposed to the case of adversarial examples. And finally, in the last part of the talk, I'm going to show you a new approach that we've been developing for improving robustness in these settings that we call model-based robust deep learning. So to start things off, let me formalize this problem setting a little bit. And to try and give an example of what these various quantities represent that I'm going to introduce, I'm going to keep this running example of variation in brightness on the Street View house numbers data set on the right-hand side of the screen. So to start, I'm going to assume that the data in my problem is distributed according to a joint distribution over X and Y. So in a classification setting, you could think of X as characterizing the distribution of images and Y as characterizing the corresponding labels in those images. So for example, in this Street View house numbers data set, X is describing these kind of images of signs, and the label is just characterizing the number that's represented in the picture. Further, I'm going to assume that there's this abstract set of environments involved in my problem. And throughout this talk, I'm going to kind of give a more concrete definition of what these environments are. But for now, you can just think of this as some subset of Euclidean space, where each point in this abstract space, EAL, describes a particular environment. And for each point in this space, so for each environment in my space, EAL, I'm going to assume that there exists a distribution XE, that represents measuring my underlying random variable pair X, Y in a particular environment. So to illustrate this phenomenon of observing a random variable in a particular environment, I'm going to kind of demonstrate it with this little cartoon at the bottom right of the screen here. So watch as I vary this environmental parameter in red, how the image in the yellow box changes. So in other words, as I change this environmental parameter E, the realization of my random variable here is changing. So the background color is changing, the image is shifting around a little bit, the contrast in the image might be changing. So in other words, the key point here is that this environmental variable E is describing some underlying unknown process that sort of characterizes how my data varies in a particular setting. And ultimately, the goal in this setting is to learn a classifier F that can well predict the random variable Y from X using only samples that are observed in a wide variety of environments. So let me add a little bit more structure to this problem. In particular, I'm going to assume that these observations of these random variables, XE, are parameterized by some unknown function G. So in other words, G is a function that takes the underlying random variable X and some environmental parameter E and maps it to some observation of X in environment E. Now to illustrate this, we can use this kind of diagram on the right-hand side. So again, we have this underlying random variable X. We push it through this map G for different environmental parameters E, and we observe this random variable in different environments. Now, if we knew this function G ahead of time, we could plug it right into a robust optimization problem, something like this, where the goal is to minimize the worst case risk over environment. So this inner maximization problem is characterizing kind of the worst case loss that you can get under your current model by changing the environmental parameter. But the caveat is, for a wide variety of applications, we don't know what this function G is. So for example, in applications where you might want to your function G to describe how the weather varies in a particular image, it's not clear how to write down a formula that particularly characterizes how weather varies. So for now, we're just going to assume G exists. And on the next slide, I'll tell you a little bit more about how you can actually obtain G in a practical application. So in particular, when we think about these kind of generative models G that are adding structure to our problem, we can break them into kind of two different cases. And I call these cases or categories known models and learned models. So let's start with known models. You'll notice that if you consider that robust optimization problem on the previous slide, I could just plug in a function like G of X comma E equals X plus E and directly recover the setting of adversarial robustness. And in particular, if I had known group structure that I wanted to be invariant to, I could just plug in the equations of that group, and then I could directly try and solve that min-max problem. But of course, perhaps the more interesting setting, and the one that I'm fundamentally concerned with in this talk, is, well, what if I don't know the form of the transformation that I want to be robust to ahead of time? So this would happen, for example, if I was trying to be robust to weather conditions or lighting, or variations in a medical imaging application. And so in these cases, when we don't have available to us a closed form expression for G, we're going to propose using unlabeled data to learn image-to-image translation networks, which are a form of generative model that can approximate this true underlying function G. And I don't have time to get into the specifics of how these generative models work in this talk, but I'm happy to talk about it offline. But just to illustrate how these work, these sorts of deep generative models that we learn to approximate G take an image X. They have some kind of deep residual structure underlying the network, which usually involves two GANs and a couple of variational autoencoders. And they're able to learn from the unlabeled data how to vary the natural conditions in images. And so again, when we don't have this function G available to us, we solve the problem by approximating G using these kind of generative models. Now let's return to that robust optimization problem that I had a couple slides ago, and let's assume that we have some G, some generative model available to us, whether it's known beforehand or whether we used unlabeled data to learn it. Now you'll notice that this optimization problem actually comprises two coupled optimization problems. So on the one hand, there's the inner maximization problem, where our goal is to maximize over this abstract space of environments to find a data point G of X comma E that's hard for our current model to classify. And on the other hand, we have this outer minimization problem where we're searching for a classifier F that minimizes the worst case risk over environments. Now, to solve this optimization problem in practice, obviously it's a highly non-convex problem, or non-convex, non-concave problem. And so we need some sort of approximate method to solve it. And in particular, we're going to propose several techniques that alternate between approximately solving this inner problem and approximately solving the outer problem. Now, the first thing to notice here is that if we already had a solution to the inner problem, we could directly optimize the outer problem using SGD, because this problem is quite analogous to a standard empirical risk minimization problem if you had samples. And so the fundamental question here is, how can I solve the inner problem? And on the next slide, I'll talk a little bit more about how we went about solving this inner problem in this paper. And in particular, what I want to do, just to illustrate this, is to give you some geometric intuition for how this problem works. So I'll move this to the top of the screen, and notice that in this problem, we start with a fixed image X. And what I want you to do is consider the following set, which I'm calling B of X, or in words, the learned image manifold. So this set B of X comprises all the images X prime that can be obtained by passing this input image X and some environmental parameter E through our generative model. So in other words, you can think of this B of X as kind of the reachable set when passing X through the model and marginalizing over the environments. Now, geometrically, this looks like some manifold in our data space, shown here in blue. And each point on this manifold is corresponding to a different image that has a different level of kind of this natural variation captured by G. So in this case, the model G is capturing variations in snow. And our goal here in solving this optimization problem at the top of the slide is to search over the set B of X to find images that are hard to classify. So to do this, we're going to propose kind of three algorithmic variants. In the first variant, we're simply going to sample k different points on this manifold and select the one that empirically gives high loss. So I might look at this point first, then I might consider this one, and finally this point. And I'm just going to select the one that empirically causes my model to have high loss. In the second approach, we're just going to perform projected gradient ascent in E over this manifold. So we might start at a fixed point here, and we move along the gradient of the manifold to try and find an environmental parameter E that's hard to classify. And finally, the last approach is simply to perform data augmentation. So I'm going to select k different points on this manifold and add them to my training set, and then go on to solve the outer problem using SGD. So before I wrap things up, let me just share one experiment with you in which we use these algorithms that I had on the previous slide. So one question that naturally arises is, when I learn one of these generative models G, can I reuse it on new data sets to provide robustness against the same sort of natural variation captured by the model? So for example, I might train a model G on this cured TSR traffic sign recognition data set, which has kind of images of traffic signs in different environments. And so the model we trained here was able to change the brightness in images. And then I could use this model to do robust training on a completely new data set, so this GTSRB, which has completely different stop signs. And we found that not only was this model able to transfer and be used on a new data set to change the brightness levels. But when we tested it, we did robust training on this GTSRB data set, we were able to improve the accuracy on these dark images by over 30%. And in the paper, we have many more experiments of this stripe, which I'd invite you to take a look at. And with that, I just want to wrap up and point you to our paper, and our code is also on GitHub if you want to play around with it. And thanks.
Thanks a lot for the talk. And I mean, let's see if there are questions in the Q&A. It seems no. So one question is, do you think this approach work really better than the standard adversarial training, and why?
Yeah, that's a really good question. So I can't seem to go back slides here, but one of the baselines that I showed on the previous slide was the standard kind of PGD adversarial training norm-bounded robustness. And that was one of the baselines that we improved upon by over 35% in that. So like the standard kind of paradigm for adversarial training deals with these kind of known perturbations, these kind of norm-bounded changes. But what we think is like in these practical applications, you can't, the changes that you are expecting, like say for a self-driving car, will not be described by norm-bounded perturbations. So the problem you actually want to solve is, well, you know, I want to be robust against kind of natural changes. And I think currently the adversarial training paradigm in the adversarial robustness community doesn't address that as well as maybe like the work that we're trying to put forward here, which more tries to you know, capture these natural distribution shifts using these generative models.
Okay, so do you expect the result will be similar to, I mean, adversarial training in case you doesn't compute the attack with FGSM, but with an unconstrained attack, a maximum confidence attack, for example? To go far. So basically, the epsilon constraints do not activate.
Sorry, I'm not sure I totally followed the question.
So the question was like, do you expect this approach is better even if you compute the attack with kind of adversarial training without an LP norm constraint?
So if the attack is done without an LP norm constraint.
Exactly.
Yeah, I would expect this attack to, or I expect our defense to do reasonably well in that setting where the attack can be potentially unbounded. If the attack is still generated by something like FGSM with respect to just an unbounded but still kind of additive perturbation, then those like standard adversarial techniques like PGD or FGSM or trades would also, I think, do a little bit better. But in the nonlinear regime where the perturbation might not be acting linearly on the data, I think that those kind of standard approaches probably would not be able to effectively defend against like unbounded nonlinear attacks nearly as well as I think the approach that we have would do.
Okay, let's thank a lot the speaker. So thanks. And let's go to the next talk, which is blocking adversarial example by testing for applicability, reliability, and decidability. The speaker is Kathrin, and that's a pre-recorded video.